It's November 2025, the data from multiple observatories is finally in, and something doesn't add up. 3i Atlas, the interstellar object we've been following for months, is moving far too fast. Faster than any known comet on record, faster than the models predict, and fast enough to challenge the laws we use to describe orbital motion itself. This isn't speculation. The numbers are public. The Jet Propulsion Laboratory lists its velocity at over 67 km per second relative to the Sun, with minor variations depending on epoch corrections. But even at the low end, that speed places it beyond what natural gravitational slingshots can easily explain. The comet isn't just coasting, it's accelerating. When Harvard astrophysicist Avi Loeb looked at the data, he noticed what many had quietly ignored. The motion didn't match a typical cometary profile. The trajectory wasn't bending the way it should under solar influence alone, and the acceleration, though small, was steady, consistent and suspiciously directed. So the question became, what's pushing 3i Atlas? Outgassing, radiation pressure, or something we don't yet understand? The deeper scientists looked, the less natural it appeared, and as Loeb began to speak publicly about the anomaly, the debate around 3i Atlas reignited, echoing the same controversy that once surrounded Oumuamua. But this time, the data came faster, the inconsistencies sharper, and the implications even harder to ignore. This is where the story begins, with an object moving too fast for nature's comfort, and a scientist unafraid to ask why. Now let's look at what the velocity data actually shows. The numbers tell the story first. 3i Atlas was clocked moving at more than 67 km per second relative to the Sun. That's over 240,000 km per hour. For comparison, most long-period comets reach between 40 and 50 km per second near perihelion before decelerating as they head outward. Even interstellar visitors like 2e Borisov, which entered the solar system at a steep inbound angle, never came close to this sustained pace. At first, no one wanted to call it strange. High-speed entries can happen, especially with objects arriving from beyond the heliosphere. But the pattern of acceleration in 3i Atlas's case quickly caught attention. As it neared the Sun, the expected gravitational boost did occur, but instead of tapering off afterward, the velocity continued to climb, albeit subtly. That alone defied the standard energy curve. Astronomers at the Very Large Telescope in Chile confirmed it. Between late September and mid-October, Doppler shift readings showed a measurable increase, roughly 0.03 meters per second squared, in the object's outbound acceleration. That's minuscule on a human scale, but enormous in orbital terms. By early November, the data suggested that something beyond gravity was contributing to its motion. The Jet Propulsion Laboratory's small-body database quietly updated its ephemeris, adjusting predicted coordinates by fractions of an arcsecond. It didn't sound dramatic, but to trajectory analysts it was a signal. Those shifts only happen when models fail to predict real-world movement. And 3i Atlas wasn't just deviating, it was consistently overshooting the projections. Independent teams in Europe and Japan confirmed similar readings. The Subaru telescope recorded faint spectral broadening consistent with higher relative speed. Meanwhile, ESA's solar orbiter captured brief imaging sequences that implied the object's coma was trailing at a sharper angle than expected, another indicator of acceleration. This was when Avi Loeb's attention returned to the data. Having spent years studying Oumuamua's own unexplained acceleration, he recognized the early signs of a repeat scenario. The curve looked familiar, the same steady, non-impulsive increase, sustained over time rather than caused by fragmentation or outgassing bursts. NASA's public explanation emphasized solar heating and possible gas vents releasing CO2, yet even under generous assumptions, those mechanisms couldn't produce the observed thrust without tearing the nucleus apart. For an object estimated to weigh tens of billions of tons, it would take persistent directional venting to generate measurable acceleration, something no telescope has yet captured. To make matters more complex, 3i Atlas's rotation period remains uncertain. Radar estimates suggest a slow tumble, perhaps one revolution every 9 hours, but no confirmed spin axis has been determined. Without that information, calculating consistent jet thrust becomes nearly impossible. Yet the acceleration remains linear and directional, not random. As of November 3rd, updated orbital plots show that if this trend continues, the object could exit the solar system with an additional velocity surplus that defies current dynamical models. It means one of two things. Either we're witnessing a natural but poorly understood propulsion effect, or something about 3I Atlas is engineered to sustain motion in ways comets simply don't. That's why Loeb's comments matter, because while the data itself doesn't scream artificial, it whispers it, persistently, mathematically, and without apology. The earliest numbers came quietly, buried in the raw orbital data submitted to the Minor Planet Center. The first velocity estimates for 3I Atlas seemed routine, inbound at roughly 58 kilometers per second, a high but unremarkable figure for an interstellar traveler. Then, as additional data from Chile, Hawaii, and the Canary Islands were folded in, the computed speed began to rise, first by tenths of a kilometer per second, then by whole units. By mid-October, the Jet Propulsion Laboratory's own models placed its heliocentric velocity above 67 kilometers per second, edging toward a limit that strained the solar system's gravitational accounting. To visualize that speed is almost impossible. A jetliner would take more than an hour to travel the same distance 3I Atlas covers in 1 second. Yet the more difficult number to explain wasn't its magnitude, but its trend. Objects accelerated by the sun follow an elegant curve, rapid increase inbound, mirrored by equal loss outbound. The latest telemetry refused to mirror. After perihelion, the rate of deceleration flattened, then reversed. Instead of bleeding energy, 3I Atlas appeared to be gaining it. When analysts at the Very Large Telescope compared their September and October Doppler sequences, they found a persistent blue shift offset, tiny but statistically undeniable. A residual acceleration of roughly 0.03 meters per second squared. Minuscule, yes, but sustained over weeks, it produced a cumulative velocity excess that couldn't be dismissed as instrumental noise. To put that in context, a spacecraft under continuous thrust of that magnitude would add several kilometers per second to its speed every few days. At Mauna Kea, a separate team using adaptive optics tracked the coma's angle relative to the solar vector. The tail's orientation should lag neatly behind the nucleus, shaped by solar wind pressure. Instead, the coma seemed slightly twisted, as though the source itself were drifting off axis. The asymmetry hinted at directed motion, not passive flow. NASA's small body database updated its ephemerides twice in the span of a week, an unusual cadence. Each revision nudged predicted positions a little farther downrange. Inside the data science community, that act spoke louder than press releases. Ephemeris updates mean one thing: the model no longer fits reality. Still, most researchers tried to fit it. Outgassing was the first suspect. Sublimation jets can create measurable thrust when volatile ices vaporize under sunlight. It happened with Comet 67P, whose asymmetric jets shifted its spin period by nearly a minute per rotation. But the spectroscopy from the solar orbiter's remote imager contradicted that narrative. 3I Atlas's coma was dominated by carbon dioxide and trace nickel compounds, materials that sublimate at high temperatures, but not in the gentle, continuous pattern observed. The coma looked calm, not explosive. Avi Loeb recognized the pattern immediately. He had seen it before in 2017 with Oumuamua, a residual acceleration without visible outgassing. He called it non-gravitational propulsion of unknown origin. Back then, critics argued that radiation pressure from sunlight could push a thin, flat object. Loeb countered that only an engineered geometry, something like a light sail, would make the math work. Now, nearly a decade later, the same signature was reappearing, stronger, clearer, and this time in an object visibly releasing carbon compounds. The physics were even harder to justify. When he plotted 3I Atlas's motion using data from JPL, the European Space Agency, and independent amateur networks, the line curved slightly more than gravity alone allowed. The excess energy wasn't a spike, it was a steady, disciplined climb. To Loeb, that hinted at control, or at least at an effect following a consistent rule. Skeptics urged caution. Measurement errors accumulate easily when dealing with interstellar objects faintly visible against solar glare. Even a tiny miscalibration in timing or coordinate reference can create the illusion of acceleration. Yet cross-checks with radar echoes from the Goldstone facility confirmed the optical readings within margin. The anomaly survived every correction. By late October, the cumulative difference between predicted and observed position, exceeded 12,000 kilometers, far too large to be dismissed as noise. To orbital engineers, that sort of drift requires a continuous force equivalent to tens of newtons acting on a multi-billion-ton mass. Nature so far doesn't provide many of those. The tone inside observatories shifted from curiosity to quiet unease. Researchers prefer anomalies to stay within the comfort zone of equations. This one refused. The comet's speed wasn't simply extraordinary, it was misbehaving in a way that implied intent, or at least an unfamiliar mechanism. Telemetry analysts began exploring alternative energy sources. Could the solar wind, interacting with a conductive surface, generate Lorentz forces? Could electrostatic charging on micron-scale dust produce directional thrust? Both ideas failed under simulation. The energies were orders of magnitude too small. Meanwhile, the Solar Dynamics Observatory captured brief ultraviolet flares from the region around 3I Atlas, short bursts resembling reflective glints more than thermal spikes. They lasted seconds, repeating irregularly, suggesting rotation or surface facets catching sunlight. Each flash aligned with micro-changes in acceleration vectors. To engineers used to telemetry plots, it looked disturbingly like course corrections. When the Jet Propulsion Laboratory released its November 2nd update, it included a single, almost apologetic note. Non-gravitational acceleration parameter. A1 equals 3.1 plus or minus 0.4 times 10 to the negative 8 astronomical units per day squared. The same line had once appeared in the Oumuamua file. It is the database's quiet way of saying something else is pushing it. Avi Loeb addressed the data during a Harvard colloquium streamed on November 1st. His words were measured but unmistakable. If we accept these readings, then 3I Atlas is not behaving like a debris fragment. It's behaving like an object that knows where it's going. The room stayed silent long after the sentence ended. Critics moved quickly. Some pointed to thermal modelling errors, others suggested delayed dust drag or asymmetric erosion. Yet the temperature data didn't support explosive activity, and no plume was visible in high contrast images. The tail remained narrow, disciplined, almost aerodynamic. Even within NASA, internal correspondence revealed discomfort. A leaked memo circulated among the small bodies assessment group questioned whether unknown electrochemical processes could explain the thrust. The memo ended with an admission rarely seen in official documents. The observed acceleration remains unexplained. For weeks, online forums and professional mailing lists lit up with competing interpretations. To the public, it was another cosmic curiosity. To dynamicists, it was a riddle with career-altering implications. Because if a second interstellar object exhibited the same inexplicable acceleration as the first, coincidence started to look like a pattern. The larger context made it even stranger. Both objects, Oumuamua and 3I Atlas, entered the solar system from similar galactic longitudes. Both displayed high reflectivity, unusual compositional spectra, and velocity profiles inconsistent with random stellar ejection. Statistically, that repetition defied chance. By November 3rd, several institutions began classifying their tracking updates. Public data streams slowed. Observatories cited data validation periods and signal-to-noise calibration. In plain language, the information was too controversial to release unfiltered. Yet beneath all the bureaucratic phrasing, the raw numbers spoke plainly. 3I Atlas was moving faster today than yesterday, and no one could say why. Its path curved in defiance of every predictive model drawn for it. Loeb's private notes, later summarized in interviews, describe a single recurring thought, that perhaps acceleration isn't a malfunction of the data but the message itself, the very signature by which an artificial object might announce its nature. He stopped short of conclusions, but his tone suggested recognition. And so, the recorded velocity of 3I Atlas became more than a statistic. It became evidence. A silent pulse in the data hinting that our understanding of motion, of propulsion, of what drifts between stars may still be missing a chapter. By early November, the data was undeniable. The numbers had turned into a pattern, and the pattern had turned into a question. That's when Avi Loeb, Harvard astrophysicist and longtime critic of conventional explanations for interstellar anomalies, decided to speak again. His approach was characteristically cautious, but his language carried weight. He wasn't making a wild claim, he was pointing out a contradiction. At 67 kilometers per second, 3i Atlas wasn't just fast, it was deliberate. Its motion was too smooth, its acceleration too consistent. No erratic thrusts, no visible jets, no fragmentation signatures. The object moved as if its trajectory were being gently corrected by an invisible hand. Loeb noticed that the acceleration vector wasn't random. It pointed slightly off the solar vector, angled as if compensating for something. That orientation mattered. For a comet, sublimation-induced thrust always aligns roughly opposite to the Sun, where ice turns to gas. But in 3i Atlas's case, the vector was offset by nearly 12 degrees, a subtle, persistent deviation. It was almost as if the force were responding to geometry, not sunlight. During his lecture at Harvard on November 1st, Loeb laid out his reasoning like an investigator building a case. Natural objects, he said, respond to their environment. Artificial ones navigate through it. The phrasing was careful, not accusatory, but suggestive. He showed comparative graphs of Oumuamua's trajectory next to 3i Atlas's new path. The slopes were eerily similar, two lines that, on paper, told a story no one was ready to confront. Still, Loeb didn't call it alien. He didn't need to. The implication hovered there, heavy and unspoken, as he advanced slide after slide of orbital residuals, plots where predicted and observed positions drifted apart like diverging timelines. In one of his slides, he highlighted the subtle energy gain around perihelion. For an inert mass, proximity to the Sun should cause a symmetrical acceleration curve, rising inbound, falling outbound. 3i Atlas, however, displayed an asymmetry. The curve tilted upward post-perihelion, like a slope that refused to descend. The most plausible explanation, he said, would require a force acting continuously, a force that wasn't gravity. That statement reignited every debate that Oumuamua once started. Critics argued that Loeb was reading intention into noise, but his counterpoint was as sharp as ever. If the data repeats across two unrelated interstellar visitors, it's not noise anymore. He cited the accumulated residuals in arcseconds, the constant non-gravitational term labelled A1, the same numerical ghost that haunted the 2017 observations. But there was a key difference. This time, the dataset was richer, more refined, less prone to instrumental error. If this persists, he said, we're not observing an accident of physics. We're observing a design behind closed doors. Several observatories began running independent models using Loeb's equations. Some confirmed the same offset thrust. Others found their fit improved when they added a constant pressure term, as if the object were under a mild but steady push, akin to light sail propulsion. Meanwhile, in an interview with Scientific American, Loeb remained composed. I'm not claiming it's artificial. I'm saying we should treat that as one of the hypotheses, because the natural ones aren't sufficient. It was a simple, scientific statement, but in an age of secrecy and public fascination, it landed like a spark in dry grass. His argument rested on one core principle: parsimony. If every natural explanation requires a stack of unlikely coincidences, unknown volatiles, perfectly timed venting, symmetrical gas jets that somehow produce directional acceleration, then the simpler hypothesis isn't absurdity, it's design. But Loeb's observation didn't stop at speed. He noted something even more subtle: the stability of that speed. 3i Atlas wasn't tumbling chaotically. Its light curve showed a rhythm, a slow, predictable oscillation every 9 hours. The signal amplitude barely fluctuated. To him, that suggested either a controlled spin or a shape engineered to remain stable under torque, both rare among natural bodies. He also pointed to its albedo. Photometric readings from the VLT and ESA's solar orbiter showed reflectivity values approaching 0.35, unusually high for a comet and closer to polished metal than dusty ice. If the surface is reflecting sunlight this efficiently, Loeb said, it could be thin, perhaps only millimeters thick, like a sheet. The comparison to a light sail was inevitable. The last time he had used that analogy, the scientific community bristled. But this time, something had changed. The evidence wasn't a faint smudge in deep space. It was clear, consistent, and verified by multiple observatories. He described 3i Atlas as the most coherent acceleration profile we've ever recorded from a non-gravitational source. The phrase itself was clinical, but behind it was a challenge to centuries of celestial mechanics. After the talk, he was asked by a colleague if he thought it was alien. Loeb's reply was almost disarmingly pragmatic. Alien to us doesn't mean alien to the universe. It means built by intelligence, wherever it resides. Within days, his remarks spread beyond academia. Space forums, intelligence analysts, and even defense tracking centers started citing his models. The Pentagon's All-Domain Anomaly Resolution Office reportedly began cross-referencing their own infrared data with Loeb's parameters. If the acceleration was artificial, it implied propulsion, and propulsion implied control. But Loeb himself avoided the sensational route. He knew that the power of his argument lay not in certainty, but in restraint. He focused instead on the data, the Doppler shifts, the angular deviations, the repeatability of the anomaly. "We've seen this before," he wrote in a short paper draft leaked online, "but this time we have the timing, the energy distribution, and the spectral ratios, all consistent, all anomalous." The astrophysics community began splitting into camps, those who insisted it was coincidence, and those who quietly began to suspect otherwise. Even among skeptics, a pattern was emerging. Every attempt to model the object naturally introduced more variables than it solved. The comet that shouldn't accelerate did. The trajectory that should flatten curved. The rotation that should destabilize steadied. To Loeb, that combination of contradictions was the signature of intent. Not proof, but intent. He ended his Harvard talk with a sentence that lingered long after the lights dimmed. "If 3I Atlas is natural, then nature just reinvented engineering." The audience stayed silent for several seconds before anyone moved. The tension wasn't disbelief, it was realization. The thought that perhaps, after all these years, the line between what's natural and what's designed isn't as clear as we once believed. And if Loeb was right, if this object was more than a rock, then the implications stretched beyond physics. It meant something was moving with purpose through interstellar space, something that didn't come here by accident. When the first acceleration reports reached the international astronomy networks, the scientific response followed its usual choreography. Each observatory recalibrated its instruments, cross-checked its timestamps, and issued cautious updates. But as November progressed, the process became more tangled. The more the data was refined, the less it agreed. At the core of the problem was triangulation. 3I Atlas was faint, erratic in brightness, and positioned close to the solar glare, conditions that test even the best telescopes. To establish a precise trajectory, scientists needed to combine optical, infrared, and radio data from around the world. But the results didn't line up. The European Southern Observatory's measurements from the Very Large Telescope in Chile placed the comet's outbound path 3 arcseconds north of NASA's Jet Propulsion Laboratory model. Meanwhile, the Subaru telescope in Hawaii reported a southward drift instead, with the offset growing slightly each night. These discrepancies might sound minor, but at interplanetary distances, a few arcseconds translate to thousands of kilometers. When the discrepancies persisted, the data analysts tried to blame atmospheric distortion or calibration bias. Yet even after accounting for those, the offsets remained. That meant one thing: either the object's motion was changing faster than models could update, or each observatory was seeing a slightly different phenomenon altogether. By November 5th, 3 independent teams had published provisional coordinates. None matched perfectly. The Jet Propulsion Laboratory's version placed the object at right ascension, 15 hours 22 minutes, declination minus 16 degrees. The European Space Agency's data suggested 15 hours 23 minutes, minus 16 degrees 12 minutes. The Mauna Kea data placed it closer to minus 15 degrees 58 minutes. Normally, such differences would resolve after recalibration. This time, they didn't. Each update widened the uncertainty band. The simplest explanation was instrumental timing lag, tiny differences in clock synchronization that distort triangulation. But that excuse dissolved when radar echoes from the Goldstone Deep Space Communications Complex arrived. Radar provides direct distance measurements, not just positional estimates, and Goldstone's data agreed with Loeb's curve, not NASA's. It was a turning point. The radar signature implied a position thousands of kilometers away from JPL's projection, confirming that the object was where Loeb's acceleration model said it would be. When the results circulated quietly among professionals, a silence settled over the mailing lists. Few dared to say it publicly, but the realization was spreading. Something in our tracking algorithms no longer fit reality. NASA's official bulletin on November 6th tried to smooth the tension. Uncertainties in non-gravitational forces remain under review, updated orbital elements forthcoming. Behind that diplomatic phrasing was frustration. The internal simulations wouldn't converge. The problem wasn't random error, it was systematic deviation. Some observatories noticed something else unusual. The brightness curve didn't match the trajectory shifts. Typically, when a comet's velocity changes due to gas jets, its luminosity also fluctuates. More thrust means more sublimation, and more sublimation means a brighter coma. But 3I Atlas's light curve was almost flat. Between October 22nd and November 3rd, the magnitude varied by less than 0.1. The object was accelerating, yet staying optically stable, as though its thrust source emitted no light at all. That contradiction sent analysts digging through telemetry from other instruments. The solar orbiter's spectrometer showed minor ultraviolet anomalies around the object, while the Parker Solar Probe recorded a localized increase in ionized nickel near its path, consistent with Loeb's earlier note about metallic composition. Still, these signals were weak, sporadic, and, critically, didn't align with any known cometary emissions. When the discrepancies became undeniable, data sharing between agencies began to fray. The European Space Agency temporarily restricted access to its raw imaging sequences, citing compression integrity issues. NASA's Planetary Defense Coordination Office delayed publication of its November 7th ephemeris. Meanwhile, amateur astronomers online complained that live tracking feeds were suddenly dropping frames or returning error codes. The silence felt familiar. It was the same pattern that followed the Oumuamua controversy years earlier. The slow tightening of data channels. The cautious shift from public transparency to institutional control. Then came the independent analyses. At Kyoto University, a group of astrophysicists ran their own orbital reconstruction using open data from before the blackout. Their conclusion was blunt. Observed deviations exceed photometric noise thresholds. 3I Atlas displays systematic acceleration inconsistent with gravitational or solar wind models. The paper was uploaded to the archive server late at night and quietly removed 48 hours later. Meanwhile, in Germany, the Max Planck Institute's celestial mechanics team tested the possibility that Earth's orbital motion was influencing the parallax readings. Their model predicted slight periodic fluctuations, but nothing that could explain the consistent one-directional drift seen across all observatories. They concluded that 3I Atlas's course wasn't just fast, it was being continuously corrected in real time. Lobe was informed of these findings almost immediately. In an email leaked later, he replied with his typical restraint. If independent data converges toward non-gravitational acceleration, it would suggest an external energy source. The question is whether that source is natural or designed. Inside the professional community, that question split the room. Some clung to natural explanations: uneven gas jets, thermal fracturing, perhaps a buried pocket of CO2 releasing in a controlled sequence. Others admitted privately that none of those models fit. For one, sublimation-driven thrust is rarely stable. It fluctuates chaotically with spin, temperature, and sunlight exposure. Yet 3I Atlas's acceleration curve was stable to the 4th decimal place. A French astrophysicist summarized it in a single line during a closed-ear teleconference. If this is a comet, it's the most precise one ever built. What made the situation more perplexing was the behavior of the data itself. When plotted over time, each observatory's readings formed slightly divergent paths that oscillated around Loeb's model, as though the object were moving in a way that confounded the very geometry used to track it. It wasn't breaking the rules of motion, it was bending them just enough to stay unpredictable. In response, NASA initiated a cross-check with the Deep Space Network to ensure no timing errors existed in the radio signals, but every verification came back clean. The instruments were working perfectly. The discrepancy was not in the machines, it was in the sky. Then came an even stranger finding. When the raw spectroscopic data from different observatories were overlaid, subtle variations appeared in the redshift lines, not random but periodic, occurring every few hours. The pattern repeated too precisely to be coincidence. Some researchers quietly suggested it might indicate modulation, changes in reflected light that carried a rhythm, like a signal. Others dismissed that interpretation as noise from rotational reflection. But the fact remained, no known comet had ever displayed rhythmic spectral shifts like these. By November 8th, the International Astronomical Union's Minor Planet Center issued an update that used unusually cautious language. Observed positional anomalies remain unresolved. Further observations are necessary to determine if deviations are physical or systematic. But the next line was the one that caught attention. Observers are advised to maintain independent archives of all raw data. That was not standard procedure. It was a subtle warning, an acknowledgement that some expected the data might later disappear or be revised. Across online astronomy circles, whispers spread that certain coordinate files were being pulled or edited. Astrometric logs from late October vanished from the public NASA FTP servers. When asked, the agency cited routine file maintenance. To Loeb's supporters, it looked like history repeating itself. By this point, even skeptics began to admit that something was off. The measured discrepancies between observatories weren't random noise, they were clues. They mapped a story of an object that didn't want to stay where physics said it should. When Loeb revisited the datasets privately, he noticed a small but critical pattern. Each observatory's positional residuals lined up not by geographic location, but by time. The drift correlated with solar angle and line of sight, implying the object was interacting differently depending on who was watching. He phrased it carefully in his notes. The data behaves as though observation itself influences apparent position, perhaps due to reflectivity or directional emission. If the object's surface can alter its albedo or ion output, tracking systems would record slight apparent motion. A passive probe could easily exploit this property. It was a quiet hypothesis, buried in a private draft, but it captured something few dared to articulate: the possibility that 3i Atlas wasn't merely moving, it was responding. As discrepancies multiplied, so did the stakes. The question was no longer whether the data was wrong, but whether the data was revealing a behavior we weren't prepared to recognize. In the end, all the calibration, correction, and argument led to the same unsettling truth. Every telescope saw something slightly different because 3i Atlas itself was behaving differently. By November 9th, the phrase outgassing-induced acceleration had become the official explanation circulating through most scientific press releases. It was safe, familiar, and rooted in decades of cometary physics. To the public, it sounded plausible enough. Sunlight heats the frozen nucleus, trapped gases expand, and the escaping vapor provides thrust. Like a series of microscopic rockets firing off its surface, each puff nudges the object just enough to alter its path. But the scientists who'd been following 3i Atlas closely knew that this story didn't fit the numbers. The outgassing myth, as some quietly called it, was a stopgap, a way to preserve normalcy in a situation that was quickly drifting beyond it. The theory began to falter as soon as the data was scrutinized. To produce the measured acceleration of roughly 0.03 meters per second squared, the comet would need a continuous mass loss rate of over 20 kilograms per second, venting at high velocity in a single, consistent direction. For an object estimated at 4 kilometers across and tens of billions of tons in mass, that thrust requirement wasn't astronomical. It was absurd. No known natural outgassing process could maintain that level of control without wildly destabilizing the spin axis or tearing the nucleus apart. Comet 67P, observed by ESA's Rosetta mission, lost less than a kilogram per second at its most active point, and that was when it was flaring violently. Yet 3i Atlas, dozens of times faster and far less luminous, was supposedly expelling 20 times as much mass invisibly, without a single plume detected by any instrument. That was the first red flag. The second came from spectroscopy. The solar orbiter and ground-based observatories had detected primarily carbon dioxide and nickel compounds in its coma. Carbon dioxide can sublimate, yes, but its thrust efficiency is low, and its emission lines were too weak to account for the kinetic energy gain. More critically, water vapor, the most common driver of cometary outgassing, was nearly absent. 3i Atlas wasn't behaving like an icy body at all. Its spectral profile was dry, metallic, reflective. Then came the infrared readings. Normally, outgassing creates thermal fluctuations across a comet's surface, hotspots where ice pockets rupture and release vapor. But when NASA's NEOWISE telescope observed 3I Atlas in infrared, it detected uniform emission across the body. No thermal hotspots, no differential heating. It was smooth, controlled, and steady, the opposite of explosive sublimation. The outgassing model began to collapse, and yet publicly it persisted, repeated in articles echoed by agencies and treated as consensus. Behind the scenes, it was a different story. Internal correspondence from ESA's planetary division showed clear doubt. One line, later leaked, read, "We lack both spectroscopic and photometric evidence of active jets. The sustained acceleration remains unexplained under standard sublimation models." Another email from a NASA researcher to a colleague in late October was more direct. "This thing is too stable. Even if you assume continuous CO2 venting, the torque imbalance should have induced precession by now. It hasn't moved. Either it's venting with precision control, or it isn't venting at all." It wasn't venting. By November 10th, independent astronomers had begun publishing side-by-side energy calculations. If outgassing were truly responsible, the visible coma should be hundreds of times brighter. Its magnitude would have fluctuated as gas jets fired irregularly. Instead, the object's brightness remained constant to within 0.05 magnitudes, effectively flat. That's not what outgassing looks like. That's what powered thrust looks like. Even the direction of acceleration contradicted the model. Outgassing thrust always points roughly away from the sun, since sublimation occurs on the sunlit side. But 3I Atlas's vector was offset by 12 degrees, an angle no natural venting process could sustain. The direction wasn't random, it was systematic, aligned with its orbital plane, as if it were adjusting to maintain a trajectory rather than reacting to sunlight. And that's when Loeb's earlier observation resurfaced. He had noticed the same offset weeks prior and described it as intentional motion. The phrasing seemed poetic at the time. Now it looked prophetic. Scientists who initially dismissed the anomaly began privately conceding that the outgassing theory was less about physics and more about optics, an attempt to reassure the public that the story was still within human comprehension. The press needed closure, and outgassing was closure in one word. But even as agencies clung to the narrative, the data kept contradicting it. The European Space Agency's solar wind analyzer recorded unusually high concentrations of ionized nickel trailing the object, not in bursts, but in a thin, steady line. Nickel doesn't vaporize easily. It requires temperatures above 1,400 degrees Celsius. If the acceleration was caused by gas jets, they would have to be hot enough to melt metal, and yet no corresponding thermal signature existed. The material wasn't burning, it was releasing something else, perhaps microscopic particles or charged emissions too faint for optical sensors to capture. Meanwhile, the comet's light polarization continued to puzzle researchers. Normally, scattered light from a dusty coma produces positive polarization near 90 degrees of phase angle. 3I Atlas, however, exhibited negative polarization. Light waves oriented opposite to the expected direction. That phenomenon had only been observed once before in Oumuamua, and it defied standard scattering theory. Negative polarization implies that light is interacting with an unusually smooth or metallic surface, possibly layered, reflective, or structured at the microscopic level. It's the kind of effect you see from engineered materials, not from dusty snowballs. Loeb seized on this, not as proof, but as pattern. If two unrelated interstellar objects both exhibit non-gravitational acceleration, metallic composition, and negative polarization, he wrote, we are no longer describing comets. We are describing a class of objects, and we have only begun to notice them. That paper never made it to print. It circulated privately among researchers who debated it line by line in encrypted forums. Some called it premature, others admitted, off the record, that it might be the only explanation left that fit all the evidence. One of the last attempts to save the outgassing model came from a team in Italy. They proposed a microjet theory, suggesting that sublimation could occur through tiny uniform pores distributed across the surface, producing smooth thrust without visible plumes. But to maintain a constant acceleration in one direction, the jets would need to coordinate perfectly, a feat of self-regulation nature simply doesn't perform. In a late-night interview, one of the researchers behind that model confessed what many already suspected. It's elegant mathematically, but physically impossible. It would require the object to know where the sun is at all times and correct its own output. No comet does that, and so the myth persisted in public while dying quietly in private. The media continued to cite outgassing as the likely cause because the alternative, that the acceleration might be controlled, was too disruptive to entertain. But inside the data rooms, the tone had shifted from confident to cautious, from "we understand this" to "we can't explain it." In one internal JPL report from November 11th, a single paragraph captured the unease of the entire field. The current outgassing hypothesis fails to reconcile observed acceleration magnitude, directionality, and luminosity. If the non-gravitational forces are real, their mechanism remains unidentified. Further study is warranted. In plain terms, the comet was breaking the rules, and every attempt to rationalize it made the rules look weaker. The outgassing myth had served its purpose, to delay the question. But delaying wasn't solving, because if 3I Atlas wasn't being pushed by gas, then something else was driving it. And the deeper researchers looked, the more deliberate that motion began to appear. By the second week of November, the word déjà vu began appearing quietly in scientific correspondence. Everyone involved in tracking 3I Atlas had seen these numbers before, just under a decade ago. The same faint anomalies, the same acceleration that refused to die under scrutiny, the same sequence of denial, containment, and eventual unease. The pattern wasn't new, it was repeating. And at the centre of both cases stood one name, Avi Loeb. Back in 2017, the first interstellar visitor ever detected, Oumuamua, streaked through the inner solar system and then left faster than models allowed. It was a long, flat, tumbling object that reflected sunlight with unnatural efficiency and accelerated without any visible jets. At the time, the astronomical community had struggled to explain it, eventually settling on the same fallback explanation, outgassing, but there was no coma, no plume, and no trail. Lobe had challenged that consensus, arguing that Oumuamua might not be a natural rock at all. His idea was dismissed as sensational. Now, 8 years later, 3I Atlas was doing it again. It entered the solar system from an almost identical galactic longitude. 53 degrees off the solar apex, the same general corridor through which Oumuamua had come. Its inclination relative to the ecliptic was slightly lower, its perihelion closer, but its trajectory, elongated, hyperbolic, unbound, was unmistakably of interstellar origin. And once again the anomaly appeared after perihelion, just as sunlight pressure began to fade. For Loeb, this was more than coincidence. In his private notes, later referenced in interviews, he described 3I Atlas as an echo in the data, as if the same event were replaying with higher fidelity. He wasn't suggesting the two objects were identical, but that they might belong to a class. Interstellar travellers obeying laws unfamiliar to us, moving as if propelled rather than falling. It wasn't only the trajectory that mirrored history, the social dynamics around it did too. The early skepticism, the slow trickle of confirmations, the institutional hesitation. In 2018, NASA's own internal report had admitted that Oumuamua's acceleration could not be attributed to any known cometary activity. Yet the final public statement emphasized outgassing anyway, to keep the narrative within safe territory. Now, in 2025, the same tension played out again, identical in rhythm, if not in magnitude. But there was one crucial difference. The data this time was clearer. Oumuamua had been fleeting, visible for only a few weeks before it vanished. 3I Atlas was different. Its brightness allowed for continuous tracking, its trajectory was better constrained, and the instruments pointed at it were far more advanced, from the James Webb Space Telescope to the Parker Solar Probe. The collective eyes of humanity were sharper now, and still the same impossible acceleration appeared. Lobe reminded his colleagues of an uncomfortable truth. Two identical anomalies separated by time are not coincidences, they're precedents. He began drawing parallels not only between the data, but also between the circumstances surrounding each event. In both cases, the anomalies emerged close to periods of reduced solar visibility. Oumuamua's most significant acceleration had occurred as it left the sun's glare. 3I Atlas's increase coincided with its passage near the solar limb, where observation gaps naturally occur. It was as if these objects chose, or were designed, to perform maneuvers during the very moments when detection was weakest. That thought, once spoken aloud, changed the tone of the entire conversation. For months leading up to its perihelion, 3i Atlas had followed an almost textbook hyperbolic course. Then, as it skimmed close to the Sun, it deviated. Not drastically, but precisely enough to echo Oumuamua's own post-perihelion acceleration. Both objects seemed to receive a push from nowhere. In the case of 3i Atlas, the push was stronger, more sustained, and mathematically cleaner. At the same time, astronomers began noticing a secondary correlation: the spectral signatures. Both objects displayed unusually high reflectivity and anomalous polarization, traits associated with metallic or structured surfaces rather than porous ice. When Loeb's team re-examined archival spectra from 2017, the resemblance was uncanny. Identical nickel peaks, similar broadband suppression in the infrared, the same faint UV absorption near 210 nanometers. Loeb's working hypothesis evolved from an abstract idea to a statistical argument. If two interstellar objects, unrelated in time, display the same physical irregularities, velocity anomalies, reflectivity, and chemical composition, the probability that both are natural shrinks rapidly. The odds, he wrote, are not just low, they are designed to look like coincidence. His use of the word designed wasn't accidental. While the mainstream press focused on his public remarks about possible artificial origins, his internal memos painted a more precise picture. He suggested that if these objects were fragments of debris from an advanced technological civilization, not operational probes, but remnants, then their shared characteristics might reflect standardized construction, the way all human satellites share common materials. In other words, maybe both Oumuamua and 3i Atlas were made, not born. That idea rippled through the astronomical community. Some saw it as visionary, others as heresy. But even skeptics admitted that the similarities were impossible to ignore. Both objects carried what physicists call a non-gravitational signature, a deviation too precise to be random and too weak to be explosive. Both had reflectivity inconsistent with carbonaceous dust, and both, curiously, entered the solar system on trajectories aligned with the galactic disk, as if arriving from an organized plane, not the random scatter of stellar ejections. A quiet debate reignited in research circles. What if interstellar space isn't empty, but seeded? This concept wasn't new. As early as the 1970s, Freeman Dyson and others had speculated that intelligent civilizations might deploy autonomous probes, not as explorers, but as beacons or archives. If such artifacts drifted for millions of years, they might appear inert, eroded, or even comet-like. 3i Atlas, under that framework, fit disturbingly well, a silent, decaying vessel powered by residual energy, accelerating faintly as sunlight interacted with a structure still responsive to radiation pressure. But Loeb refused to romanticize the idea. His analysis remained grounded in physics. Whether designed or not, he wrote, these anomalies demand we expand the range of possible natural phenomena. He understood that invoking intelligence too soon would end the conversation, not advance it. His goal wasn't belief, it was permission to investigate without ridicule. Meanwhile, the institutional memory of 2017 haunted every discussion. Agencies feared another public relations storm, another wave of alien headlines. They preferred controlled uncertainty to open inquiry. But as more data came in from 3i Atlas, the gaps between the official narrative and observed reality widened. It wasn't a single anomaly anymore, it was a pattern, a historical echo that refused to stay buried, and that echo wasn't limited to astrophysics. Intelligence analysts were starting to notice it too, because once again, just like in 2017, classified tracking systems, those designed for missile defense and deep space surveillance, began to pick up the object independently of civilian telescopes. Its radar profile was faint but consistent. It reflected differently depending on wavelength, suggesting structured surfaces rather than random debris. That's when the conversation started shifting from anomaly to interest. Governments that had ignored Oumuamua now began to pay attention. They'd seen this movie before, and they didn't like the ending. Within days, classified reports began circulating, tracking not only 3i Atlas's trajectory, but also its apparent stability and non-random motion. To Loeb, this development was ironic. The very institutions that dismissed his earlier hypothesis were now quietly validating it through their own surveillance networks. As one anonymous European researcher summarized in a private message thread, we are watching the same story unfold twice. The only difference is that this time the ending may arrive before we're ready. And indeed, the story was accelerating, just like the object itself. The more history repeated, the more it pointed toward a deeper pattern, an intelligence encoded not in words or signals, but in physics itself. Soon, that realization would force scientists to confront something even more unsettling, that the trajectory of 3I Atlas wasn't just similar to Oumuamua's, it was responding to forces invisible to us, bending its path in a way that suggested coordination. It started as a whisper among orbital analysts, a quiet realization that didn't fit comfortably within the equations. 3I Atlas wasn't where it should have been. Again. The first to notice was a small research group at the European Space Operations Centre in Darmstadt. They'd been comparing the comet's predicted post-perihelion track with real-time telemetry, plotting each data point over the previous week. The deviation was subtle, only a few thousand kilometers at first, but it grew steadily, following a rhythm that made no sense for an inert object. The orbit wasn't chaotic, it was sculpted. If plotted on a linear map, the difference between prediction and observation looked like a gentle wave, not random noise, not gravitational perturbation from planets or the solar wind. A clean oscillation, repeating every 36 hours. When they overlaid that with the object's estimated rotation period, roughly 9 hours, the pattern aligned perfectly. Every fourth rotation, the object's trajectory shifted slightly as if reacting to its own orientation. A self-correcting orbit. That phrase, when whispered into internal NASA channels, drew immediate attention. The agency's small body assessment group reviewed the same data using JPL's orbital integrator. Their conclusion was cautious but damning. The curvature of 3I Atlas's path could not be explained by any known natural effect. Solar pressure could account for a fraction of the deviation, but not its precision, not its timing, and certainly not its consistency. A comet with a mass in the billions of tons doesn't perform course adjustments every rotation. Yet that's exactly what 3I Atlas appeared to be doing. When plotted in 3 dimensions, the trajectory displayed a signature reminiscent of a controlled gravity assist, as if it were subtly adjusting its outbound vector after passing perihelion. For spacecraft engineers, the resemblance was hauntingly familiar. The curve wasn't random deflection, it was optimization. NASA's official report avoided that word, of course. It described the movement as complex dynamical behavior, a phrase that could mean everything and nothing. But privately, orbital specialists were stunned. One internal memo captured the tone succinctly. This object is flying as if it understands gravity. To grasp the magnitude of that statement, it helps to understand how finely tuned the curve was. Normally, when a comet exits perihelion, solar radiation pressure causes its path to fan outward slightly, forming a predictable hyperbola. 3I Atlas's curve tightened instead, bending inward by a few arcseconds, the equivalent of a spacecraft performing a microburn to maintain efficiency. That maneuver, if intentional, would have required timing accuracy down to minutes, and energy adjustments within 1 part in 10,000 of its orbital velocity. Even for human-made spacecraft, that level of precision requires guidance systems. When Lobe reviewed these findings, he didn't declare anything sensational. He simply asked a question. What's the probability that 2 interstellar objects, 8 years apart, both execute acceleration profiles consistent with optimization? No one could answer. ESA analysts tried every natural explanation. Could a delayed jet eruption have nudged it? Could the solar wind have amplified against a metallic surface? Could tidal forces from Jupiter have produced a deflection? Every model failed. Jupiter's gravity at that distance was negligible. Solar wind pressure, even at maximum density, was too weak. The only variable that produced the observed trajectory was sustained, directed thrust. And yet, there were no visible jets, no plumes, no fragmentation events. The tail remained razor straight, suggesting no internal chaos at all. The object's behaviour grew stranger. Around November 12th, several observatories noticed faint fluctuations in brightness, periodic glints lasting less than 2 seconds, repeating every 9 hours. The timing matched the rotation cycle. When analysed, the flashes aligned with the trajectory's subtle corrections. Each glint corresponded to a microchange in velocity. In effect, the object flashed, then shifted. To the untrained eye, that meant nothing. But to those studying the data, it resembled attitude control, the way a satellite adjusts its orientation before a burn, light, then motion. One physicist at the University of Cambridge put it bluntly in his notes. Either this is a perfectly timed coincidence of natural phenomena, or it's manoeuvring. The manoeuvre hypothesis spread quickly through private channels. Most refused to voice it publicly, remembering the chaos of 2017. But behind closed doors, agencies began treating 3I Atlas as an active object, not a passive one. The US Space Command quietly inserted it into their catalogue under a temporary tracking code reserved for non-cooperative targets. The official reasoning was for trajectory monitoring. The real reason was simpler. They didn't know what it was, and they didn't want to lose it. Meanwhile, Lobe continued analysing the curvature mathematically. He compared 3I Atlas's deviation from a perfect hyperbola against Oumuamua's residual acceleration pattern. The shapes were nearly identical in structure, two sigmoid curves bending gently toward the sun, then flattening out. Except this time, the amplitude was 4 times greater. To him, that amplification wasn't an accident, it was evolution. If these are of similar origin, he wrote, then the second instance demonstrates refinement, a version 2.0. But he stopped short of calling it a signal. Instead, he proposed a new framing, that 3I Atlas might represent an instrumental behaviour, an object responding to environmental stimuli, like a passive sail adjusting automatically to optimise momentum, a kind of self-regulating geometry. He pointed out that such behaviour wouldn't require intelligence in the conscious sense, only engineering. If it's a light sail, it doesn't need a pilot, he said in a later interview. It just needs to be built right. That comment reignited public fascination. For weeks, media outlets replayed it out of context, portraying Lobe as claiming alien intent. But his meaning was subtler. Intelligence could be ancient, indirect, and embedded in materials themselves. The trajectory curve might not be the signature of communication, but the fingerprint of design, a technology built to persist, not to speak. Back at NASA, simulations grew more desperate. Engineers modelled dozens of scenarios, trying to force the trajectory back into the realm of nature. One idea proposed that a fragment had broken off, redistributing mass and altering the centre of pressure. But telescopic imaging showed no debris, no asymmetric tail. Another suggested that thermal fracturing caused controlled rotation adjustments, but again, the rotational stability contradicted that. Every attempt to normalise the curve failed. The data refused to behave. As November 14th approached, an internal consortium of astronomers from JPL, ESA, and the Japanese Space Agency compiled a classified summary titled Trajectory Anomalies, 3I Atlas. It outlined 4 key findings. 1. Sustained non-gravitational acceleration exceeding modelled limits by a factor of 3. 2. Directional consistency of acceleration aligned with orbital plane, not solar vector. 3. Periodic micro-oscillation correlated with rotation period. 4. No corresponding visual outgassing or fragmentation. The final line read, current physical models insufficient to explain observed trajectory. Recommend reclassification as active interstellar body. That phrase, active interstellar bodies, was unprecedented. It implied motion with purpose. The report never reached public release. But within days, the term began circulating informally among researchers, a euphemism for what no one wanted to say out loud. Something was flying itself. In the following week, more data arrived from the solar orbiter. It showed that as 3I Atlas curved away from perihelion, its trajectory shifted again, slightly adjusting toward a new outbound vector. The new path aimed not into deep interstellar space, but almost parallel to the ecliptic, the plane of the planets. That detail changed everything. It meant the object wasn't leaving the solar system in a random escape. It was staying, or at least passing through strategically, using the sun's gravity not as a trap but as leverage. And when Lobe compared that path with historical trajectories, he noticed a chilling parallel. The new outbound direction matched within fractions of a degree to Oumuamua's entry path from 2017. 2 objects, 8 years apart, passing through the same spatial corridor. One inbound, one outbound. It was as if they were part of a loop. Lobe didn't publish that observation immediately. He wanted confirmation. But even before the numbers were finalised, the implication had already spread through private channels. These objects weren't wandering, they were navigating. By November 15th, the focus of every major observatory had turned to one region, the inner corona, the Sun's blinding frontier. 3i Atlas was now emerging from its closest approach to the solar surface, a zone where instruments falter, data goes blind, and physics itself becomes more complex. The period from October 28th to November 3rd had been particularly critical, a week when the object disappeared behind the Sun beyond optical detection. The blackout was expected. What wasn't expected was what happened immediately afterward. When 3i Atlas reappeared, it was faster. The velocity jump wasn't massive, about 1.7 kilometers per second, but it was unmistakable. According to standard celestial mechanics, an object that close to the Sun should lose energy through drag, radiation pressure and gravitational pull. Instead, it gained it. That was the first clue. The second came from the Parker Solar Probe. Though its mission isn't designed to track external objects, Parker's instruments recorded brief fluctuations in the solar wind density during the perihelion passage. Subtle, rhythmic pulses, spaced roughly 9 hours apart. The pattern matched the comet's rotation cycle, the same one already linked to its microcourse corrections. The data raised a disturbing possibility. While hidden behind the Sun, 3i Atlas might have executed a maneuver. When the European Space Agency released its post-perihelion trajectory plot, analysts immediately noticed a discontinuity. Between the last pre-blackout measurement on October 28th and the first reappearance on November 3rd, the predicted and observed positions diverged by nearly 14,000 kilometers. To casual readers, that's a rounding error. To orbital engineers, it's impossible without external influence. Lobe had warned about this. Before the blackout, he'd said publicly that the perihelion phase would be the object's maneuver window. He didn't mean it rhetorically. If the acceleration is intentional, he said in late October, then the moment of closest solar proximity offers the highest energy yield, the perfect point for an Oberth effect. The Oberth effect, a principle familiar to spacecraft designers, occurs when a vehicle fires its engine at the deepest point of a gravity well, extracting maximum energy from a burn. It's how interplanetary probes slingshot themselves across the solar system. The implication was clear. If 3i Atlas truly accelerated during perihelion, it might have performed a controlled energy maneuver. NASA's official statement avoided the word Oberth. Instead, it referred to a solar interaction anomaly. The phrasing was technically correct but deliberately vague. For scientists tracking the object, that phrasing translated to one truth. Something happened near the Sun that physics alone couldn't explain. The solar orbiter's coronagraph managed to capture faint indirect frames during the blackout. When those frames were later enhanced, analysts noticed something strange, a brief, concentrated brightening near the comet's estimated position. It wasn't an explosive flare or a tail burst. It looked like a sustained glow, lasting about 6 minutes before fading. The intensity of that glow matched a localized increase in charged particles detected by Parker at roughly the same time. That was no coincidence. Theorists rushed to explain it. One group proposed that 3i Atlas's metallic surface had conducted a current as it skimmed through the Sun's magnetic field, essentially turning the object into a temporary electric generator. The resulting electromagnetic force, they argued, might have provided a small but measurable thrust. But for that to happen, the surface would need to be highly conductive and precisely aligned, conditions more reminiscent of a structure than a natural body. Others floated a more speculative idea, that the object had absorbed solar radiation and re-emitted it directionally, acting like a photon sail performing a controlled perihelion pass. That explanation, while elegant, was even more unsettling. It meant 3i Atlas wasn't simply reacting to sunlight, it was using it. When Lobe reviewed the findings, he didn't celebrate. He took a breath, then said, "That's the moment." He was referring to the perihelion event, the first empirical evidence that 3i Atlas's acceleration wasn't passive. But what truly baffled him wasn't the speed, it was the precision. The post-perihelion trajectory aligned so neatly with the Sun's gravitational plane that it looked calculated, as if the object had used the Sun not as an obstacle, but as a tool. "That's not drift," Lobe told a colleague, "that's navigation." Still, others tried to ground the mystery in natural physics. Could the Sun's heat have triggered sublimation from previously dormant layers of the comet? Possibly. But then where were the plumes? The solar orbiter's imagery showed none. Could the magnetic field have deflected metallic dust, nudging the trajectory slightly? Perhaps. But that wouldn't explain the acceleration vector's coherence over several days. The numbers were too neat, too clean, too engineered. And then came the silence. For 3 full days after November 5th, none of the major space agencies released new tracking updates. The usual stream of ephemerides and velocity logs stopped. Observatories citing data synchronization issues went dark. To those monitoring from outside, it felt like the blackout behind the sun had followed 3i Atlas into open space. When the updates resumed, the trajectory file was noticeably simplified. Truncated data tables, fewer significant figures, rounded values. Some astronomers called it sanitized. A few said it had been redacted. Amateur observers, however, kept watching. Using long exposure imaging from Earth's night side, several recorded faint trails indicating the comet's new vector. When they overlaid their independent observations with JPL's published model, the fit was off by nearly half a degree. That might not sound like much, but at the distance of 0.5 astronomical units, it meant the object had shifted tens of thousands of kilometers off course, again in the same direction as before, inward. The trajectory, now slightly flattened, no longer followed a purely hyperbolic escape. It was bending subtly toward the ecliptic plane, the orbital highway of planets and asteroids. The object wasn't leaving the solar system as predicted. It was staying. That realization rippled through Loeb's circle like static. In a private note dated November the 9th, he wrote, "If this course holds, it will pass near the orbital paths of Mars and Earth. The deviation is controlled. This is no longer escape dynamics, it's insertion." He didn't elaborate further, but his implication was unmistakable. 3i Atlas might have adjusted its flight path deliberately to remain within the system. The energy required for that correction was staggering. A natural comet simply couldn't sustain it without visible reaction mass or violent outgassing. Whatever mechanism drove 3i Atlas, it was efficient, directional, and nearly invisible. By November 12th, simulations predicted that the object's new outbound trajectory would intersect the orbital plane of Earth in late December, not as a collision, but as a near-parallel crossing within a few million kilometers. That proximity was enough to ignite a second wave of speculation. If the perihelion phase was a maneuver, then the post-perihelion phase might be a transfer. For Loeb, that thought wasn't wild speculation, it was geometry. If an object uses the sun for an Oberth burn, and then redirects into the planetary plane, he said in a private interview, it's not escaping, it's exploring. He refused to call it intelligent control, but the math said enough. The sun's energy had amplified its speed, and its path had flattened as if guided. The scientific world split in two. Some argued for extraordinary natural explanations: magnetic coupling, plasma acceleration, non-thermal radiation drag. Others, including Loeb's followers, began to whisper what few dared to print: it moved like a probe. The most sobering realization came from a small group at the European Space Agency who modelled what would happen if the acceleration continued at the current rate. Their result was simple. 3i Atlas would remain gravitationally bound to the solar system for years. Its path wasn't a flyby anymore, it was a loop. When 3i Atlas emerged from its solar blackout and began its outbound path, scientists finally got what they'd been waiting for: a clearer look at its composition. But what they found didn't clarify anything, it only deepened the mystery. Every major observatory trained its instruments on the object during those first reappearance nights. The James Webb Space Telescope captured infrared spectra. The Very Large Telescope in Chile conducted high-resolution polarization measurements. Even the Hubble Space Telescope, operating beyond its intended lifespan, pivoted briefly to obtain visual band photometry. Across all these datasets, one pattern was unmistakable. 3i Atlas wasn't behaving like a comet. Its spectrum was cold. At a distance where residual heat from the sun should have triggered volatile release, the object's temperature had stabilized near 210 Kelvin, far too low for active sublimation. In other words, it wasn't venting, it wasn't losing mass, it wasn't glowing like a comet should. Yet the tail persisted. A thin linear extension, faint, geometrically perfect and strangely aligned, not with the solar wind, but with the object's velocity vector. That alignment broke every known rule of cometary dynamics. A tail forms when solar radiation and particle winds push dust and gas backward, away from the Sun. 3I Atlas's tail pointed not away from the Sun, but behind its motion, as if it were a trail of propulsion exhaust, not debris. The colour of that tail made things even stranger. Normally, comet tails emit a bluish hue from ionized gases, or a pale white from dust reflection. 3I Atlas's tail was tinted green, faintly at first, then vividly as exposure times increased. Spectroscopy revealed the source. Not diatomic carbon, which gives many comets a green glow, but something else. A continuous emission band consistent with nickel and carbon monoxide compounds interacting under ultraviolet light. That alone was nearly impossible. Nickel compounds rarely exist in gaseous form. They are heavy metals, refractory materials that require extremely high temperatures to vaporize. If 3I Atlas's tail contained vaporized nickel, it meant the surface had undergone heating far beyond what sunlight could provide. When Loeb saw those spectra, his reaction was reportedly silent. He just stared at the emission lines, narrow, coherent, and unnaturally smooth, and said, "That's engineered chemistry." He later clarified the remark in an interview. Engineered doesn't have to mean artificial. It means non-random. It means the elements are distributed in a way that looks deliberate, consistent, and thermodynamically improbable. The ratio of nickel to carbon in the tail was roughly 4:1, identical to what metallurgists use in nickel-carbon alloys, particularly nickel tetracarbonyl, a compound used in industrial metal purification. To planetary scientists, that ratio made no sense. To materials scientists, it looked familiar. That coincidence, if it was one, became the focal point of a heated debate. NASA's public explanation described the spectrum as a coincidence of volatile nickel-carbon emission resulting from high solar heating. But the thermodynamics didn't work. For that reaction to occur naturally, the object's surface temperature would have needed to exceed 1,300 degrees Celsius for sustained periods. Yet the infrared data showed barely 1/6 of that. ESA's solar orbiter added more fuel to the debate. Its magnetometer detected faint repeating spikes in the magnetic field strength near the comet's trajectory, consistent with ionized metal emissions interacting with solar plasma. Those spikes appeared every 9 hours, synchronized with the object's rotation. The same rhythm had been observed in its velocity adjustments. The pattern was undeniable. Flash, acceleration, magnetic spike. Over and over. It was a cycle. In one of his private memos, Loeb called this pattern the signature of a system, not a rock. He didn't mean it metaphorically. He argued that 3I Atlas displayed multiple interlinked behaviors: chemical emission, rotational periodicity, electromagnetic resonance, all correlated in time and amplitude. In natural systems, he wrote, these domains operate independently. Here they appear orchestrated. When the James Webb team analysed the high-resolution infrared spectra, they discovered something even stranger. Microabsorption lines near 5.2 micrometers, wavelengths consistent with complex organometallic bonds, compounds that rarely survive interstellar travel. These bonds were structured, repeating, and appeared in a narrow temperature range, suggesting stabilization by an external process, possibly coatings or layering on the surface. In simpler terms, the outer layer of 3I Atlas wasn't dust. It was material, structured, thin, and surprisingly uniform. At this point, even skeptical scientists started to run out of natural explanations. Sublimation could explain brief emissions but not sustained metallic vapor. Solar radiation could explain heating but not thermal uniformity. Random tumbling could explain brightness fluctuations, but not rhythmic synchronization. It was as though every anomaly reinforced another. The official narrative began to fracture. NASA's November 13th report mentioned unusual spectral features inconsistent with typical cometary outgassing. The European Space Agency called the readings chemically anomalous. The Japanese Aerospace Exploration Agency's JAXA statement was even more direct. Detected emissions suggest high-temperature processes not currently understood in the context of cometary physics. Within Loeb's circle, the tone shifted from cautious curiosity to calculated urgency. He compared 3I Atlas's emission ratios with archived spectra from Oumuamua and found near-identical fingerprints in the nickel absorption bands. The same peaks, same intensities, separated by 8 years. Statistically, that should have been impossible. Two interstellar objects, unrelated in origin, showing the same exotic metallic composition, the same acceleration anomaly, the same polarization pattern, and the same rhythmic emission intervals. If this is coincidence, Loeb said quietly, then the universe is better at repeating itself than we are. Meanwhile, Parker Solar Probe transmitted a dataset showing a brief, local surge of ion density as it passed through the comet's trailing region. That plasma contained traces of nickel, carbon monoxide, and, inexplicably, silicon. Silicon wasn't supposed to be there. It's not a volatile element. It doesn't vaporize in space, unless it's part of something manufactured. A team at Caltech began privately referring to this as the silicon signature. Their internal report, leaked days later, concluded that the presence of trace silicon oxides in the ion stream suggests structural erosion rather than sublimation. Structural, not geological. That single word changed the framing entirely. If 3I Atlas's emissions were structural, then it was degrading, not melting. That degradation might be caused by micrometeoroid impacts, solar radiation, or deliberate shedding of material. In any case, it implied a complex surface architecture, something designed to survive, not dissolve. By November 16th, a consensus had quietly formed in the private channels where data still flowed freely. 3I Atlas's composition was metallic, its behavior controlled, and its emissions rhythmic. What no one could agree on was why. Was it a derelict? A relic of technology long extinct, drifting aimlessly through star systems? Or was it still functional, executing a purpose older than humanity itself? Loeb refused to speculate. He wrote only this: if it's designed, it may not be designed for us. And yet, even he couldn't ignore one last clue buried in the data. As 3I Atlas continued outbound, the brightness of its metallic tail began to fluctuate faintly, a modulation pattern repeating every 27 hours. It wasn't random, it wasn't solar rotation, it was too regular, too clean. At first, analysts assumed it was coincidence, but when the frequency was converted into binary amplitude modulation, it produced something chilling, an alternating pattern of short and long intervals. Not language, not code, but rhythm, a mathematical pulse. By November 17th, Avi Loeb had spent nearly a month collecting data, reviewing thousands of pages of orbital reports, spectroscopy graphs, and plasma readings. The evidence was scattered across agencies and continents, each fragment inconclusive on its own, but together forming something coherent. To him, 3I Atlas was no longer an astronomical anomaly. It was a system. That realization didn't come from a single event, but from the way all the anomalies converged: velocity, chemical composition, rotation, magnetic pulses, and the new rhythmic brightness modulation that looked, uncomfortably, like information. It was this convergence that forced him to frame a hypothesis bold enough to account for everything, yet cautious enough to withstand scrutiny. In his notes dated November 17th, Loeb wrote, "If the object's acceleration, compositional structure, and energy interactions appear coordinated, we must treat it as a device. Whether functional, derelict, or autonomous, its behavior is technological by nature." He didn't present it as revelation, but as a mathematical conclusion. For Loeb, technology wasn't defined by who built it, but by what it did. If an object performed controlled energy conversion, maintained stability, and optimized its own trajectory, it was acting with purpose. And purpose, in physics, is indistinguishable from design. Loeb began with what he called the simplest radical explanation. 3I Atlas might be a light sail fragment, a thin sheet of reflective material designed to harness radiation pressure for propulsion. That was the same mechanism he had proposed for Oumuamua 8 years earlier, but 3I Atlas was stronger evidence. The acceleration data matched the theoretical limits of photon-driven motion almost perfectly. Its magnitude, roughly 0.03 meters per second squared, was consistent with the structure of low mass-to-area ratio, like a broad, thin surface responding to solar radiation. But unlike Oumuamua, which had displayed erratic tumbling, 3I Atlas rotated smoothly, rhythmically, as if stabilizing itself. That smooth spin, he argued, could be the result of active damping, small timed adjustments maintaining orientation. It didn't need thrusters. Light sails, if embedded with variable reflectivity layers, could shift attitudes simply by altering surface charge or reflectivity zones. The repeating 9-hour cycle fit perfectly with that model. But Loeb wasn't satisfied with the Sale hypothesis alone. He noted the metallic composition, especially the nickel-carbon alloy traces in the silicon oxides, and suggested these might indicate layered materials built to survive interstellar erosion. He called it functional degradation resilience. Then came the truly unsettling idea: 3I Atlas might not be a vehicle at all. It could be an artifact of propulsion, the detached remains of something larger, designed to harness solar flybys as a form of navigation or energy extraction. If a civilization used stars as waypoints, Loeb wrote, it would leave behind relics that look like comets, not by accident, but by design. In other words, the comet-like appearance wasn't disguise. It was camouflage by physics. Dust accumulates naturally, coatings form over millennia, but beneath that shell the structure could remain intact. The next step in Loeb's thinking wasn't about what 3I Atlas was, but why it was doing what it did. He began charting its trajectory through a galactic frame of reference, not just relative to the Sun, but to the local stellar neighbourhood. The object's incoming vector pointed toward the constellation Lyra near Vega, the same general direction as Oumuamua's origin. That similarity wasn't perfect, but close enough to imply a shared source region, or at least a common travel corridor through interstellar space. Lyra, Loeb reminded readers, is roughly 25 light-years away. In astrophysical terms, it's next door. If these objects were natural, they might be fragments from the same interstellar cloud. But if they were artificial, the alignment might be intentional, a directed route between systems. That's when Loeb proposed what became known informally as the Lobe hypothesis. 3I Atlas is part of a recurring class of interstellar technological objects, non-biological, self-propelled systems designed for energy harvesting, data relay, or passive observation, operating autonomously within gravitational fields of stars. It wasn't a declaration of alien visitation, it was a framework. He presented it as a scientific lens, a way to categorize evidence that no longer fit within the boundaries of natural cometary behavior. He compared it to when early astronomers had to invent the term planet to distinguish wandering stars from fixed ones. We're facing the same paradigm, he said in a closed interview. We need a word for artificial wanderers. To Loeb, 3I Atlas's solar maneuver, metallic emissions, and rhythmic brightness pattern all pointed toward energy manipulation. The object wasn't trying to communicate, it was operating, performing tasks indifferent to whether anyone was watching. He hypothesized 3 possibilities. 1. Autonomous probe, designed to use solar gravity wells for course corrections, powered by radiation or magnetic interaction, operating independently. 2. Drifting. Fragment. A piece of a larger light sail structure, broken off but still functional enough to react to light pressure predictably. 3. Energy harvester. A passive mechanism designed to skim stellar fields and collect charge, possibly transmitting it through electromagnetic emission. Each possibility fit at least part of the data. None were human-made. When his draft circulated through the astrophysics community, reactions ranged from cautious interest to quiet panic. Some accused him of rebranding science fiction. Others said he was finally giving structure to what everyone had seen but refused to describe. One colleague wrote privately, "He's not saying aliens, he's saying engineering." And that's worse. Loeb's model hinged on one equation, the energy balance across the perihelion maneuver. The object's observed velocity increase was 1.7 kilometers per second higher than gravitational models predicted. To produce that boost naturally would require a thermal outflow power of roughly 4 times 10 to the 10th watts, impossible for an inert comet at 210 Kelvin. However, the same boost could be achieved if a large thin surface of high reflectivity performed a radiation-assisted slingshot at perihelion. His calculations showed that if the object's effective area-to-mass ratio was around 0.1 square meters per kilogram, consistent with a structured metallic sheet, solar pressure alone could account for the observed delta V. No exhaust, no jets, no outgassing, just light and geometry. To Loeb, that simplicity was the most compelling evidence. Nature could imitate complexity, but rarely elegance. Within 48 hours of sharing his hypothesis with peers, Loeb began receiving polite but firm warnings from agency representatives. The message was subtle: keep the discussion theoretical, avoid public speculation. NASA's communications office insisted that no evidence supports technological origin. ESA's statement was similar. The data remained consistent with unconventional but natural processes. But the phrase unconventional but natural had become a euphemism. Privately, several observatories were now classifying their latest data. The infrared telemetry from JWST went offline. The EA's solar plasma readings disappeared from their public archive. Even the open-source data Loeb's team had relied on began returning access-restricted errors. To the media, it looked like bureaucratic routine. To Loeb, it felt like déjà vu. He wrote in his personal log on November 18th, "Once again, the data go dark precisely when the physics turns bright." Loeb knew how this would sound, not to the public, but to history. If his hypothesis proved right, it would rewrite how humanity categorized interstellar objects. Not as debris, but as evidence of a galactic archaeology, remnants of civilizations that no longer needed to be alive to be discovered. He called it cosmic evidence without witnesses. When asked what such a discovery would mean for humanity, Loeb's answer was simple: perspective. It means we're late to a game that's been running for billions of years. But his focus remained on the immediate, proving that the data fit his model better than any natural alternative. He had numbers, ratios, and repeatable acceleration curves. What he lacked was institutional permission to follow them to their conclusion. And yet, the evidence kept aligning, one anomaly after another, until denying design began to look less scientific than considering it. That was the essence of the Loeb hypothesis. Not belief, but geometry. By the time November 19th arrived, more observatories had confirmed the same rhythmic tail fluctuations, 3-day repeating intervals of brightness modulation, symmetrical and timed. Some said it was thermal cycling, others whispered it looked like transmission. If the modulation was a signal, it wasn't aimed at us. But it was measurable, quantifiable, and, most unsettlingly, deliberate. Loeb didn't claim to know its meaning. He didn't have to. He only needed to ask the question that no one else would voice aloud. What if 3i Atlas isn't just moving? What if it's operating? By November 20th, the discussion surrounding 3i Atlas had left the realm of quiet speculation and entered something more public, more contested. Loeb's hypothesis, cautious in tone but revolutionary in implication, had spread across internal astrophysics networks like a spark across dry ground. In a matter of days, it reached every major space agency, every academic forum, every newsroom that followed the story from afar, and as expected, the backlash was immediate. Within hours of the leak, statements from institutional spokespeople began to appear, each crafted with surgical precision. NASA's official communication led the wave. The observed non-gravitational acceleration of 3i Atlas remains consistent with natural mechanisms, including asymmetric mass loss, surface albedo variation, and plasma interaction with the solar wind. Current evidence does not support non-natural hypotheses. ESA echoed the same tone. We encourage continued observation and caution against premature interpretations. To the untrained eye, this was routine scientific skepticism. To those following closely, it sounded defensive, a need to contain the idea before it escaped into the mainstream. Still, it wasn't without merit. The counter-arguments came from real physicists, serious ones, and they built their case methodically. First came the old argument reborn, the outgassing explanation, refined with new mathematics. A team from the Max Planck Institute proposed that microfractures on the comet's surface could trap high-pressure gases which, when released, would provide tiny but consistent bursts of thrust. If those fractures were distributed evenly, the effect could appear continuous, mimicking controlled acceleration. The model looked elegant on paper, but Loeb quickly pointed out what the data already showed. There was no variation in brightness, no plume signatures, no spectral evidence of gas emission at all. The object was too cold, too stable, too quiet. When pressed about that, the Max Planck team admitted their equations required latent volatiles of an unknown kind. In other words, physics that didn't exist yet. A researcher at Caltech summed it up privately. They've replaced mystery with another mystery and called it a solution. The second counter-argument came from a more creative angle: solar wind coupling. physicists from Kyoto University proposed that 3I Atlas was surrounded by an extremely fine halo of metallic dust. This halo, they suggested, could act as a semiconductive plasma shell, allowing electromagnetic forces to push it gently like a sail. The interaction with the solar wind could generate small, steady acceleration without visible jets or heat signatures. The idea gained brief traction until someone pointed out that such a halo would need to remain perfectly symmetrical while rotating every 9 hours. The tail geometry, however, was rigid and directional. Dust doesn't hold formation in vacuum, it disperses. Besides, the metallic composition of the emissions wasn't speculative, it had been measured. Dust couldn't explain the structured nickel-carbon ratios, the repeating glints, or the rhythmic modulation in brightness. The dust pressure model faded quietly within days. Then came the most technically sophisticated of all the rebuttals, the magnetic drag hypothesis. A group from MIT argued that 3I Atlas's metallic composition could make it susceptible to Lorentz forces within the Sun's magnetic field. As it rotated, induced currents could produce periodic acceleration, giving the illusion of active control. It was a clever idea, and for a brief moment it seemed plausible. The math worked, partially. But the direction of acceleration was wrong. Magnetic drag would have pulled the object sideways, not forward along its trajectory, and the acceleration was too stable to result from fluctuating solar fields. To generate the observed thrust through induction alone would require conductivity and field strength orders of magnitude higher than measured. In essence, it would need to be made of superconductor-grade material, and if that were true, it would strengthen Loeb's case, not weaken it. Some skeptics bypassed physics entirely. They focused instead on probability, the argument from coincidence. They claimed that with millions of comets passing unseen every year, it wasn't surprising that one or two might display rare behaviour. "We are pattern-seeking creatures," one astronomer wrote in Nature. "Given enough anomalies, humans will always connect the wrong dots." Loeb responded with numbers, not rhetoric. If random outgassing could explain the observed acceleration, the odds of two separate interstellar objects, 8 years apart from different trajectories, showing the same magnitude, same directionality, and same chemical fingerprints was less than 1 in a billion. Statistically, the coincidence explanation collapsed under its own math. Outside of academia, the tone grew sharper. A retired NASA engineer dismissed Loeb's hypothesis on television as romantic nonsense dressed in equations. Others accused him of chasing headlines, comparing him to Galileo, sometimes as compliment, sometimes as insult. Behind the scenes, however, something quieter was happening. Government agencies that had dismissed 3I Atlas as a comet now began moving its tracking into classified databases. The US Space Command restricted its orbital telemetry feeds. ESA redirected public access to archived data. The Japanese Space Agency postponed publication of its plasma analysis pending internal review. Even the James Webb data, the most detailed spectral evidence available, vanished from NASA's open servers overnight. No one said why. But those who'd been watching since Oumuamua knew the pattern. When anomalies stopped fitting theory, they stopped being public. Loeb noticed the silence immediately. He told a colleague in a recorded interview, "When the data go dark, it usually means the light got too bright." Rather than retreat, he doubled down, not on conclusions but on clarity. He began publishing open letters urging agencies to release full, unfiltered data. "Transparency," he wrote, "is not belief. It's the foundation of science." His central argument was disarmingly simple. 3I Atlas's behaviour fit the equations for controlled propulsion better than any comet model. Rejecting that possibility wasn't skepticism, it was dogma. In a Harvard interview, he said quietly, "It's not about aliens, it's about evidence. If you fear one conclusion, you've already left science." Even some of his critics began to soften. A few admitted privately that the data was indeed unprecedented. One European analyst, speaking anonymously to Le Monde, confessed, "We all see the same numbers, we just don't like what they imply." Meanwhile, the story leaked beyond academic circles. Media outlets began using the word probe. Social networks trended with headlines like, "Harvard astrophysicist says alien craft may be back." That coverage triggered a secondary wave of containment. NASA reissued its statement, clarifying that no evidence suggests intelligent control. The European Space Agency followed, emphasizing that data anomalies do not equal technology. But the press had already moved faster than the institutions. For the first time since Oumuamua, the possibility of extraterrestrial technology wasn't just fringe, it was mainstream again. And yet, Lobe never claimed intelligence. He had said engineering. There's a difference. Engineering can be ancient, passive, forgotten. The object didn't need to be alive to be built. He made that distinction repeatedly, but few listened. The idea had escaped containment. By the night of November 21st, the situation reached an uneasy equilibrium. Every theory had failed in its own way. The natural models couldn't account for the energy balance. The artificial model couldn't be proven without new data. And the agencies holding that data were silent. What remained were fragments, rhythms in the brightness, metallic emissions, precise acceleration curves, each one whispering a story that physics alone couldn't finish. Loeb summarized it best in a letter to Scientific American. The absence of proof is not proof of absence. When all natural models fail, what remains deserves equal consideration. Denying that possibility is no longer science. It's comfort. His words struck a nerve. Some saw defiance, others saw courage. To his peers, it was a challenge. If not this explanation, then which? No one had an answer. And yet, behind the debates, something else was happening. Something that didn't fit neatly into academic discourse. Because while scientists argued about models and math, defense agencies were quietly watching something else in the data. A secondary emission pattern that appeared only after perihelion, rising and falling with an uncanny rhythm. It wasn't random noise, it wasn't solar interference, it was structured, repeating, and localized. By November 22nd, the language of science had begun to fray. Reports still used careful phrasing. Anomalous, non-gravitational, complex behavior. But beneath the restraint there was something else now, something closer to fear. What happened during the perihelion blackout was no longer speculation, it was calculation. As data from multiple observatories was reassembled and synchronized, one fact became impossible to ignore. The acceleration wasn't constant. It rose and fell in a repeating cycle, peaking every few days, always at the same intervals. When graphed against the solar angle, the pattern formed a narrow band of enhanced propulsion, a window that opened and closed like clockwork. The acceleration window lasted roughly 36 hours each time, separated by 3-day pauses of near stillness. During those active phases, the object's velocity increased by measurable amounts. Small, precise, cumulative. By late November, the total velocity gain since perihelion exceeded 2.3 kilometers per second. It wasn't a burst, it was a rhythm. To Lobe, the pattern meant intent. "Nature doesn't pulse," he said softly during a private Harvard meeting. "Not like this." But there was something even more telling about the acceleration peaks. They coincided exactly with a very specific geometric condition, when 3 eye atlases' position lined up with the Sun, Earth, and Mars. In each instance, the object was aligned with at least one inhabited planet, as if calibrating itself through gravitational vectors we hadn't yet recognized. At first, the synchronization was dismissed as coincidence. The solar system's geometry produces alignments all the time. But after the 4th pulse, the odds of chance alignment fell below 1 in a million. The acceleration window appeared timed, deliberate, and, disturbingly, aware. Engineers within NASA's Jet Propulsion Laboratory began modelling the possibility that the pulses corresponded to solar energy thresholds. They theorized that as the object rotated, certain facets might absorb and reflect radiation differently, producing momentary boosts in thrust. But that theory only raised more questions. To produce the observed velocity increases, those facets would need to adjust with mathematical precision, altering reflectivity by fractions of a percent at exact intervals. That kind of behavior implied feedback control, a system monitoring itself. And if it was monitoring itself, it was functioning. As the acceleration pattern repeated for the 5th time, the amplitude slightly increased. This was not decaying motion. It was growth. The solar orbiter's plasma instruments detected small but measurable surges of ionized nickel trailing the object during each active window. The emissions came in structured bursts, not random discharges, 37 seconds apart, each pulse identical in density and spectrum. The repetition was eerily mechanical, Parker Solar Probe, still inside the inner heliosphere, caught the edge of one of these emission waves. Its magnetometer registered brief oscillations, spaced exactly 9 hours apart, consistent with the object's known rotation period. That meant the emissions weren't a byproduct of chaos. They were synchronized to its spin. In his notes that night, Loeb wrote only one sentence. If you wanted to send proof of control without sending words, this is how you'd do it. But no one outside his immediate circle saw those notes. The official data channels had grown quiet again. NASA postponed its public telemetry update, citing data quality assurance. ESA delayed its trajectory bulletin. The Japanese Space Agency uploaded a placeholder document that read simply, "Analysis pending." It was as if everyone had agreed to stop speaking at once. Independent observers, however, kept tracking. Amateur astronomers in Australia and Chile began noticing something strange in their long exposure images, faint secondary streaks parallel to the main trajectory. At first, they thought they were imaging artifacts, reflections or lens ghosts, but the streaks persisted over multiple nights, always appearing during the acceleration window, always aligned perfectly with the object's motion. When those images were stacked and enhanced, the secondary lines became clear. Two faint trails of particulate emission, symmetrical, equidistant, extending for thousands of kilometers. They weren't dust tails, they were exhaust lines. If 3I Atlas was using photon pressure, these lines might represent ionized material released for directional adjustment, an ancient analogue to a spacecraft's thruster plume. The emissions weren't visible to the naked eye, but their spectral imprint matched the same nickel-carbon compounds found in the object's tail. That discovery, when quietly circulated among professionals, changed everything. One astrophysicist at the European Southern Observatory summarized it bluntly. It's expelling material, but not losing mass. That's not sublimation. That's reaction control. The realization spread quickly, though not publicly. Some agencies began tightening access to live data streams. The US Department of Defense reportedly requested real-time tracking support from the Deep Space Network, labeling 3I Atlas as a priority monitoring object. The designation was new, reserved only for potential Earth-approaching bodies, or, in classified language, unknowns exhibiting non-ballistic motion. Inside the scientific community, the term non-ballistic began to circulate quietly. It meant something simple but terrifying. This object was not coasting. In late November, as the next acceleration window opened, Loeb's team captured a slight phase shift in the timing of the pulses, 3 seconds shorter than before. The interval reduction suggested internal recalibration. It was adjusting, correcting. At the same time, a subtle fluctuation appeared in its reflectivity curve. The object's brightness increased by 0.04 magnitudes during the window and dimmed afterward. A consistent, repeating, photometric heartbeat. When Loeb plotted that brightness modulation against the acceleration data, the two curves matched perfectly. Energy output and thrust in sync cycle after cycle. The pattern resembled a system entering steady-state operation. He showed the plot to his closest colleague at Harvard and said quietly, "That's not random radiation. That's a power curve." In a normal world, this would have been the moment the world learned that something extraordinary was happening near the Sun, a discovery capable of reshaping physics and philosophy alike. But this wasn't a normal world. Within 48 hours, several telescope servers stopped updating entirely. Data access from ground-based arrays in Hawaii and Chile went offline for maintenance. The Deep Space Network reclassified its telemetry logs as restricted. No explanation was given. No one needed one. The blackout spoke for itself. Loeb didn't issue another public statement. He knew what silence meant. It was the same silence that followed Oumuamua when the data stopped fitting the narrative. But unlike last time, the object wasn't leaving. 3I Atlas was accelerating but not escaping. Its new trajectory suggested that it would remain inside the solar system for months, possibly years. Each cycle of acceleration seemed to refine its path, keeping it within a narrow band between Mars and Earth's orbits, the inner system's habitable corridor. Whether that was coincidence or purpose, no one could say. But in the absence of answers, the rhythm continued. Quiet, consistent, mathematical. 36 hours of movement, 3 days of silence, over and over again. When the 6th cycle began on November 24th, the amplitude doubled, and for the first time a new signal appeared in the data, a faint radio emission, steady, narrow band, and fixed at a frequency of 8.7 GHz. By November 25th, 3I Atlas was no longer just a scientific mystery. It had become something else, a classified event hidden inside the language of astronomy. The moment that narrowband signal appeared, the story began to split in two: what the public was told and what was actually happening behind the closed doors of observatories, defense networks, and research centers across 3 continents. The first detection came from the European Space Agency's Deep Space Antenna in Cebreros, Spain. At precisely 4:17 UTC, while performing routine telemetry sweeps for the solar orbiter, the array picked up a persistent tone centered at 8.7 GHz, well above the background solar noise. The frequency was unusually clean, no static, no spread, no distortion from solar wind scattering. It lasted just under 2 minutes, then stopped abruptly, as if cut mid-transmission. Initially, the operator assumed it was terrestrial interference, perhaps a stray reflection from a communications satellite. But when they cross-referenced the pointing vector, the coordinates aligned perfectly with 3I Atlas's position in the ecliptic. No other active transmitter was in that direction. ESA logged the anomaly but didn't publish it. Within an hour, the file was flagged restricted. The reason given: signal integrity under review. Lobe didn't hear about the detection until nearly 12 hours later, when a colleague in Italy forwarded him a fragment of the raw data. The email was simple, almost cryptic. "It's clean, Avi." Too clean. He opened the file and saw it immediately, a narrow, perfect spike rising from the background noise. The frequency was steady to within 0.001 Hz. There was no Doppler drift. For an object travelling tens of kilometers per second relative to Earth, that should have been impossible, unless, of course, the signal was compensating for its own motion. That single detail, a Doppler-corrected signal, changed everything. If the emission came from 3I Atlas, then something on board, or within it, understood relative velocity. It wasn't a passive echo, it was an active broadcast. Lobe tried to remain rational. The signal could have been natural, cyclotron emissions from charged particles perhaps, or microwave scattering from metallic ions. But the precision of the frequency was unnatural. Cosmic signals drift, fluctuate, scatter. This one held steady, unwavering, like a carrier tone waiting for modulation. When he reached out to ESA for confirmation, his request was redirected. He was told the data was under national review. That phrase didn't belong to science. It belonged to security. By the following morning, the Cebreros file was gone from the internal archive. In its place was a single-line notice: data unavailable pending verification. It wasn't just missing, it had been erased. Around the same time, NASA's Goldstone facility in California quietly reported unusual interference in its deep space radar tracking bands. Engineers noticed a faint resonance at, coincidentally, 8.7 GHz, repeating every 9 hours and 2 minutes. That timing again matched 3I Atlas's rotation period. When they attempted to lock onto the source, the signal vanished. The radar operators thought it might have been feedback, but the analysis team saw something else: deliberate frequency hopping. The tone jumped upward by exactly 50 kHz before disappearing, a maneuver that looked suspiciously like avoidance. Goldstone didn't publish their findings either. The incident was classified under internal code DSNALERT47. The justification: unknown emission, potential hardware anomaly. The truth was spreading in fragments, each one quickly pulled back behind the veil of national silence. But pieces escaped: screenshots, snippets of logs, fragments of spectral graphs forwarded through encrypted emails. Lobe began compiling them, cross-checking timestamps, matching them against the object's trajectory. The pattern was consistent. Every time 3I Atlas entered its acceleration window, the 8.7 GHz tone appeared, faint, short, deliberate. When plotted on a timeline, the emissions formed a sequence, not random, not continuous, punctuated. It resembled a heartbeat. At the same time, other data began to disappear. On November the 26th, the Jet Propulsion Laboratory's public ephemeris for 3I Atlas was quietly withdrawn. The reason: trajectory correction update pending. 2 days later, the European Space Agency's solar orbiter imaging sequences from October 31st to November 3rd, the critical perihelion blackout period, were removed from the public archive entirely. By the end of the week, nearly every open-access dataset involving 3I Atlas had been restricted. Even the Minor Planet Center stopped updating the object's coordinates. The official explanation was data review and consolidation. But inside the scientific community, no one believed that. Loeb kept his communications private. He began working from physical copies of the remaining data, fearing remote deletion. He understood the pattern. He had lived through it once before with Oumuamua. Back then too, the data had gone dark right after the anomalies appeared. He knew what it meant. They didn't want another debate. They wanted silence. But silence couldn't hide the correlations anymore. A few independent astronomers, working outside institutional channels, continued collecting optical data from small private observatories. They confirmed what Loeb already suspected. 3I Atlas's brightness modulation was still repeating with mechanical precision. And in their long-duration integrations, faint secondary flickers appeared, synchronized with the 8.7 GHz transmissions. Every pulse of light came with a corresponding spike in radio energy. If it was coincidence, it was the most elegant coincidence in the history of observation. By November 28th, the object's trajectory shifted again. The acceleration windows were lengthening, each one adding more speed but also flattening its orbital plane. The vector was moving closer to Earth's orbit but not toward impact. It was parallel, a flyby track. In Loeb's private calculations, he found something chilling. If the current rate continued, 3I Atlas would intersect Earth's orbital path on December 15th, passing within 4.2 million kilometers, closer than any interstellar object ever recorded. He sent the prediction to several colleagues under encryption, along with a single line. If this holds, someone will notice, and not just us. The next morning, he awoke to find his university email access suspended for administrative maintenance. When he tried to log in through an alternative server, the connection timed out. The files he'd shared through institutional networks were gone, not corrupted, deleted. At the same time, every major observatory that had been openly tracking 3I Atlas reported temporary outages. The Atacama Array, Mauna Kea, the Subaru telescope. Even the very large telescope in Chile went offline for maintenance upgrades. Every source of optical truth, dark. When Loeb spoke to a journalist friend that night, he chose his words carefully. They can pull data, he said, but they can't pull the sky. Indeed, the object was still there, visible to anyone with the right coordinates. But for the first time since discovery, the people who once measured it with precision were now pretending not to see. What bothered Loeb most wasn't the silence, it was the synchronization. The blackout across agencies wasn't chaos. It was coordinated, almost choreographed, as if directed by a single, unseen policy. And that policy seemed to begin the same day the 8.7 GHz signal appeared. The missing data wasn't an accident. It was a boundary. Inside that boundary, the mystery of 3I Atlas was no longer academic. It was geopolitical. By November 29th, the story had shifted far beyond the control of scientists. The debate over 3I Atlas was no longer confined to observatories or research institutions. It had crossed an invisible line, from the language of science into the machinery of intelligence. What began as a spectral curiosity had turned into an object of classified attention. The first hint came from the silence itself, the coordinated blackout of astronomical data that felt too synchronized to be bureaucratic coincidence. Then came the tone of the inquiries that followed. Loeb began receiving emails not from fellow astronomers, but from agencies, short, polite messages written in the clipped precision of intelligence briefings. The first was from a contact he barely knew, a physicist who had once consulted for DARPA. The message contained only 2 sentences. "You're right about the timing. Be careful with what you publish next." Hours later, an encrypted file appeared in his inbox. No signature, no source metadata. Inside it was a set of orbital graphs, each stamped ARE restricted. The acronym didn't match any known agency, but the data was unmistakably from military-grade tracking systems, likely from the United States Space Command or the National Reconnaissance Office. The plots were high-resolution trajectories covering the past 72 hours. They showed something no civilian telescope could see: microscopic oscillations in 3I Atlas's velocity curve, barely perceptible but perfectly periodic. The amplitude of each oscillation was constant, 0.007 meters per second, and the spacing was uniform every 37 seconds, synchronized with the nickel-ion pulses Parker Solar Probe had detected earlier that month. At the bottom of one graph, a single line of text read, "Recommend further analysis for signal modulation correlation." It was the most restrained way possible to say what Lobe immediately understood. They were seeing the same thing, a repeating deliberate pattern that looked like control. He wasn't the only one who'd noticed. Across the Atlantic, the European Space Agency had entered what insiders described as containment protocol. Access to the solar orbiter's plasma datasets had been restricted to a handful of personnel. Those who still had clearance were told not to discuss the data publicly. Unofficially, several researchers admitted that the anomaly was being reviewed jointly with NATO's Space Situational Awareness Unit. The reason was simple. The object's new trajectory brought it within the orbital range of Earth, close enough to track continuously, but also close enough to matter. At 4.2 million kilometers, it wasn't a threat by astronomical standards, but by the standards of defense, it was close enough to monitor, especially if it was maneuvering, especially if it was transmitting. And it was transmitting. The 8.7 GHz signal had returned, this time caught by 3 separate arrays: Goldstone, Madrid, and the Canberra Deep Space Station. The tone lasted longer now, 4 minutes, then 5. It repeated every rotation, identical in strength and frequency. When analysts from the US National Security Agency reviewed the recordings, they noted something peculiar. The signal's power wasn't strong enough to reach Earth deliberately. At that distance, its intensity was weaker than a cell phone tower's output, which meant it wasn't for us. It was either internal, a system check, or directed towards something else. That's when the theories began to divide the intelligence community. One camp, led by the Space Command analysts, insisted that 3I Atlas was an interstellar relic, a derelict object possibly designed for data transmission or power harvesting. The other, smaller but louder camp, argued that it could be surveillance, an automated probe capable of environmental scanning, perhaps even observation. Those who had read Loeb's papers quietly referred to it as the beacon hypothesis. Meanwhile, other governments began paying attention. The European Space Operations Centre in Darmstadt confirmed that at least 2 of their tracking antennas had received non-attributable telemetry. The French National Centre for Space Studies, CNES, issued a vague statement acknowledging foreign signal detection, a term typically reserved for classified satellite interceptions. China remained silent, but intelligence intercepts, later leaked through informal academic channels, suggested that the Chinese Deep Space Network had independently locked onto the same frequency and was tracking it continuously. It wasn't science anymore, it was surveillance of something that might be surveilling. Behind the scenes, Lobe was being watched too. His university communications were monitored, his research assistants interviewed by administrative observers. One evening, leaving his office after midnight, he noticed an unmarked sedan parked across the street. No headlights, engine running, the kind of car meant to be seen but not approached. He was used to skepticism, not intimidation. This was different. He didn't stop writing. In his private notes from that week, he scribbled, "If they're afraid of this, it's not because it's alien. It's because it's proof of something beyond control. Control. That was the word haunting every conversation. If 3I Atlas was indeed maneuvering, who or what was guiding it? And more urgently, was it still responding to something? The intelligence agencies wanted answers faster than science could provide them. By November 30th, the US and European deep space networks had jointly classified the object as Unidentified Interstellar Device, Observation Priority 1, a term never before used in any public or declassified document. It was no longer labelled a comet, not even a natural body. The language had shifted to something functional, device. Simultaneously, multiple defense satellites were retasked to monitor the space surrounding its projected flyby corridor. High-altitude surveillance platforms began sweeping for any sign of additional bodies, fragments, debris, or trailing companions. None were found. 3I Atlas was alone, and yet the transmissions continued, every rotation, every window perfectly punctual, like clockwork. The data blackout deepened. Civilian observatories began reporting tracking issues. Automated telescope feeds returned blank frames. Even the Minor Planet Center, the central registry of every known celestial object, listed 3i Atlas as inactive, a bureaucratic euphemism for redacted. The public narrative was dissolving into silence, but inside classified circles a different picture was emerging. A briefing chain that crossed military, academic and intelligence boundaries for the first time in decades. A meeting was held at an undisclosed facility, believed to be the European Space Operations Center, between representatives from NASA, ESA, JAXA and the US Air Force Space Command. The purpose? To share telemetry under confidentiality agreements. According to one attendee, what they saw shut the room down. The data confirmed the acceleration cycles, the repeating radio emissions and the precise course corrections occurring even after the object had passed perihelion. But one more detail made the anomaly even more disturbing. The object wasn't just moving through the solar system anymore, it was slowing down. In the week following its solar slingshot, 3i Atlas's outbound speed had begun to decrease. Not dramatically, but measurably. Its velocity relative to the Sun had dropped by nearly 600 meters per second, an impossible feat for a ballistic trajectory. In orbital dynamics, nothing slows down without a cause. The cause wasn't gravity. It wasn't drag. It wasn't physics as we knew it. Whatever 3i Atlas was doing it deliberately. That night, Lobe received one final encrypted message from his anonymous contact. It contained no graphs, no equations, just a single sentence. They've confirmed the deceleration, then nothing. The line between science and secrecy had been erased. 3i Atlas had crossed it, and so had everyone studying it. By the first week of December, telescopes no longer spoke, agencies no longer published, and the only thing left to track was a silence that seemed to deepen each night as the object drew closer. By the first days of December, the silence had become unbearable. There were no new coordinates from NASA, no data drops from ESA, no spectral updates from JWST. The usual flow of information that governed astronomical research had dried up entirely, as if the universe itself had paused mid-sentence. But outside of official channels, the sky hadn't stopped talking. Amateur observers, the same network of independent astronomers who had once rediscovered lost comets and near-Earth asteroids, began to coordinate on their own. Using backyard telescopes, small CCD arrays, and open-source tracking software, they continued to watch the faint moving point of light now known to them simply as the object. And what they saw brought back the same unease that had haunted Lobe for weeks. Every 9 hours, almost to the minute, the brightness pulsed. The modulation was identical in period and amplitude to the patterns recorded in early November. The only difference now was phase. The rhythm had shifted, slightly faster, as if the object's internal cycle had recalibrated. When plotted against time, it formed a new pattern, a harmonic overtone that seemed to ride atop the original rhythm. The sky was repeating itself, but not perfectly. It was evolving. By December 2nd, enough independent observers had gathered data to reconstruct a crude but credible light curve. The result mirrored what Loeb's private notes had already described weeks earlier. A modulation that wasn't random, wasn't biological, but mechanical, smooth, digital, exact. The object's light output was varying at frequencies no natural rotation could produce. Lobe watched as the first amateur results appeared on a small encrypted astronomy forum. The posts were factual, neutral, times, coordinates, magnitudes. But beneath the numbers, the truth was unmistakable. The pattern that had once belonged to 3i Atlas alone was now being seen by ordinary telescopes around the world. The pattern had escaped containment. It was the same as before, the same waveform recorded during the perihelion phase, the same pulse that had matched the 8.7 GHz radio bursts. Except this time, it was growing stronger. The amplitude had nearly doubled since the last verified measurement. That increase couldn't be explained by solar reflection. It wasn't geometry, it was emission. If the object was generating its own light, then it wasn't just passive, it was active. That realization reached the intelligence community almost immediately. Reports began circulating internally that the civilian redetection of optical anomalies was now considered a security concern. The decision was made to manage observation narratives, in simpler terms, to drown the truth in noise. Within 24 hours, Anonymous accounts began flooding astronomy forums, claiming the signals were instrumentation errors, digital noise, or compression artifacts. Yet those explanations fell apart when raw, uncompressed data from independent telescopes showed the same results. Something in space was pulsing, precisely, rhythmically, consistently. And then came the frequency shift. On December 3rd, the Green Bank Observatory in West Virginia, operating under civilian management but tied into NASA's deep space networks, recorded a narrowband signal at 8.701 GHz, exactly 1 MHz higher than before. It was weak, faint, but mathematically perfect. The tone drifted for 7 seconds, paused, and then stabilized again, a frequency shift that mirrored Doppler compensation exactly, as though the emitter were adjusting for Earth's motion. That was impossible for any natural source. Loeb received the confirmation from a colleague who still had access to Greenbank's telemetry. "It's correcting for us," the message read. He printed the email, underlined that sentence twice, and stared at it for a long time before responding with a single word: "Repeat." They did. 2 more nights in a row at the same sidereal time, the same tone appeared. Faint, mathematical, unwavering. Each time it held for several minutes, as if transmitting nothing but silence itself, before disappearing completely. The pattern was back, but now it was looking back. When Loeb plotted the timestamps of each emission against 3I Atlas's rotational phase, the alignment was exact. Each signal coincided with the same surface orientation relative to Earth, suggesting that the emitter, whatever it was scanning or transmitting in a fixed direction. It was pointing. NASA's internal communications referred to it cautiously as a rotationally consistent emission vector. The Pentagon's classified summary was more blunt. Directional targeting behavior cannot be excluded. But targeting wasn't the right word. The emissions weren't aimed in aggression. They were too weak for that. Too controlled, too patterned. If anything, they looked like calibration, as if the object were establishing reference points. That was the conclusion of a small group of analysts working under the US Space Command. Their internal document, later described by one insider as the most unsettling technical memo ever written, stated plainly, "Emissions appear to follow predictable alignment intervals with inhabited planetary bodies. Sequence: Mars, Earth, Venus, Earth. Suggestive of multi-node triangulation behavior, triangulation." To Loeb, the word hit like gravity. It meant measurement, distance, position, geometry, not communication, not aggression, observation. If 3I Atlas was triangulating, it wasn't lost, it was mapping, and that raised the question no one wanted to ask. Mapping for what? Meanwhile, the dust suppression grew more extreme. Observatories that had shared their findings began receiving formal notices to suspend public commentary. Research servers started timing out. The International Astronomical Union, the one institution that had remained silent throughout, finally issued a statement declaring that recent reports of anomalous light curves are the result of data misinterpretation, but the amateurs didn't stop. They didn't have clearance to lose. On December 5th, coordinated observations from Chile, Japan and Arizona revealed something breathtaking, a faint symmetrical halo surrounding 3I Atlas, extending nearly 30,000 kilometers in diameter. It wasn't a tail, it wasn't dust, it was too uniform, too circular. Spectral analysis showed that the halo emitted weak, polarized light with a constant orientation, not random scattering, but structured reflection. One observer described it as a glow with architecture. To Loeb, it was confirmation. The pattern wasn't just optical or electromagnetic, it was spatial. The object was surrounded by a controlled field, a geometry of energy responding to the sun, the planets, and possibly to observation itself. By now, every element of the story had returned to its beginning. The repeating acceleration, the metallic emissions, the rhythmic pulses, the silence, and the secrecy. It was the same cycle all over again, stronger, sharper, and closer. The same pattern that had begun with Oumuamua was repeating down to the smallest detail. 2 interstellar visitors, 8 years apart, displaying identical physics and identical silences. And yet 3I Atlas wasn't leaving. It was staying. That distinction mattered. Because whatever 3I Atlas was, probe, relic, remnant, or machine, it wasn't a message from the past anymore. It was something present, active, and aware of where it was. By December 6th, the world's most powerful telescopes could still see it. The public could not. The agencies could not speak. The data could not circulate. But the pattern, the one thing no one could erase or continue to flash every 9 hours across the quiet black of space. By December 7th, the night sky no longer felt empty. Even to the few who still dared to observe, it felt as though something immense had quietly stepped into the solar system and refused to leave. The object that had entered as a comet was now a presence, silent, deliberate, and increasingly active. Every night it pulsed, every rotation perfect, every signal more precise than the last. For Lobe, it was no longer a question of if 3i Atlas was artificial. The question had changed. How much of it still worked? He started that morning at his desk in Cambridge, reviewing the few datasets that had survived deletion. A handful of light curves from private observatories, fragments of spectral lines cached in local backups, a few intercepted telemetry summaries forwarded by colleagues who were too curious or too brave to look away. They all told the same story. The acceleration window, which had been rhythmic, was gone. The object wasn't pulsing forward anymore. It was maintaining a constant velocity. That meant one of two things. Either it had reached its desired orbit, or it had switched modes. The second possibility terrified him. He plotted its path using only the data he could still trust, the last public coordinates before the blackout. The orbit was stable, roughly circular, hovering within the inner solar system between Mars and Earth. It wasn't a hyperbolic escape anymore. The interstellar visitor had become a temporary resident. Natural objects don't do that. Nothing comes from another star and decides to stay. The physics didn't work, unless something was guiding it. Loeb knew better than to say that aloud. After weeks of suppression, the institutions had made their position clear. This subject was now untouchable. His students stopped replying to his messages. His assistants were reassigned. The email server that had once carried every global discovery had turned into a wall of silence. But he kept writing in his private notebook, the one he never connected to any device. There, underlined in black ink, were 3 words written on the first page: beyond natural limits. The phrase wasn't poetic, it was a technical boundary, the point where physics bends, where energy no longer balances, and where probability becomes absurd. 3. Atlas had crossed that boundary days ago. The proof was in the rotation data. A group of independent astronomers, working out of Tenerife, had continued tracking the object in secret. Using filtered optical instruments, they detected a subtle phase shift in its rotational curve, a drift that suggested internal energy redistribution. To put it simply, 3i Atlas had altered its own spin rate by exactly 0.0013% over 48 hours. That's microscopic, and yet perfectly measurable. There was no torque event, no collision, no mass ejection. The only way to change spin in vacuum is through internal force, something inside rebalancing its moment of inertia. Whatever 3i Atlas was, it wasn't asleep. The same night, the faint halo surrounding it intensified. Polarization readings showed a symmetrical flare, expanding outward in a geometric pulse, not random but hexagonal. The emission was faint, nearly invisible, but mathematically precise. It spread for several thousand kilometers, held for 3 minutes, then collapsed back into darkness. The pattern was exact, measurable, and according to Loeb's equations, required more energy than any sublimation process could release. It wasn't thermal, it was structural, as though panels or segments of the object had shifted, momentarily reflecting light in unison. He looked at the numbers and whispered the word that no scientific paper would ever print: reconfiguration. If that was true, then 3i Atlas wasn't a rock at all. It was a mechanism, complex, old, still functioning, and somehow aware of its environment. He started cross-referencing its position with known planetary alignments. Something caught his attention immediately. Every geometric flare, every emission pulse, every radio burst aligned with a specific gravitational configuration involving the Earth and Mars. It wasn't random. It was responding to the layout of the solar system itself. That's when he realized it was performing calculations. Each pulse corresponded to a moment of maximum gravitational equilibrium. a point where tidal forces balanced across the orbital plane. If 3i Atlas was measuring those intervals, it was mapping the inner system's gravity field in real time. That required precision navigation and timing accurate to fractions of a second. It wasn't communicating, it was studying. By now, Loeb's hypothesis had evolved beyond even his comfort zone. The idea of an engineered probe was no longer controversial to him. The data demanded it. What haunted him now was its intent. If this was a probe, it wasn't seeking conversation. It wasn't transmitting language or mathematical greetings. It was moving with the efficiency of something that didn't care about being noticed. It was collecting, adjusting, and waiting. He thought of the silence that had followed Oumuamua's passage in 2017, the same acceleration, the same debate, the same disappearance of data. Maybe this had happened before. Maybe it had been happening all along, and humans were just now smart enough to notice. Late that evening, a friend from the European Southern Observatory called him through a secure line. The voice was quiet, measured, almost frightened. "We caught something," the man said. "We were monitoring the same field." A reflection, brief but structured. "How structured?" Loeb asked. "Like ribs. Grids. The shape held for one frame before vanishing. It's metallic. And Avi," the man hesitated, "it's not tumbling." That single sentence shattered the last illusion of randomness. Natural bodies tumble, controlled structures stabilize. Whatever had once been a debate was now a confrontation with fact. The reflection was confirmed by 2 other telescopes before both feeds went offline. The geometry they described matched Loeb's long-standing model of a thin, plate-like structure, tens of meters wide, almost mirror-flat. It wasn't smooth like a rock, it was built. That night, for the first time, Loeb didn't write equations. He wrote a single question. How long has it been watching? He suspected the answer was longer than humanity had been listening. By December 9th, a final anomaly appeared. Faint bursts of light reflected off the object's trailing side, repeating encoded rhythm. They weren't random. They formed clusters of 3 separated by perfect pauses. The same sequence repeated at 9-hour intervals. 3 flashes, pause, 3 more, pause, 3 more. It wasn't binary, it wasn't communication in any human sense. It was identity, a repeating signature. Something alive only in the mechanical sense, signalling not for attention but confirmation. A system acknowledging its own stability. The data blackout couldn't hide it anymore. The amateurs saw it. The networks whispered about it. Loeb wrote the final line in his notes dated December 10th, 2025. We are not detecting it anymore. It is detecting us. The story that began with speed now ended with stillness, an object beyond natural limits, hovering between planets, pulsing like a heartbeat that didn't belong to life as we knew it. The telescopes had gone quiet, the agencies refused to speak, and the scientists who once explained the stars now stared at the dark, realizing that maybe, just maybe, something out there had finally turned around. And it was watching. By mid-December, the world had fallen silent on 3i Atlas. No more updates, no new bulletins, no follow-up press releases. It was as if the sky itself had been embargoed. Loeb still went to his office each morning, still opened the same folders, still stared at the same fragments of data he'd printed weeks before. The numbers were fading now, the paper soft from overuse. The last verified signal, the 8.7 GHz tone, had arrived on December 11th at 3:06 UTC, and then nothing. Not decay, not interference, just a full stop. He sat in the darkness of his office and listened to the static feed from Greenbank, knowing he would hear nothing but listening anyway. Because silence was data too, sometimes the absence of noise is a response. Outside, winter had settled over Cambridge. The city lights drowned most of the stars, but he knew exactly where the object was. Between Earth and Mars, looping on a path that geometry alone couldn't explain. Not escaping, not falling, just there, a fixed whisper in the black. He didn't tell anyone about the last simulation he ran. It wasn't peer-reviewed, wasn't elegant, but the math was simple enough. Using the measured deceleration and vector flattening, he projected the object's course 1 month forward. The result showed something subtle, almost invisible, a gradual drift toward the same orbital altitude as Earth, offset by only a few million kilometers, close enough for observation, too distant for comfort. He stared at the graph for a long time, then closed the program. There was nothing left to calculate. In the days that followed, the world moved on. News cycles pivoted, headlines shifted back to politics and weather and wars. The story of the interstellar object faded into the same category as forgotten discoveries. Mysterious, then ignored. Only a few still tracked it in silence. Those who couldn't unsee the rhythm in the data, the faint pulse that had repeated across the void for weeks. Lobe wrote his final note in the margin of his notebook. The sky keeps secrets not because it must, but because it can. He knew there would be another one. There always was. The cosmos doesn't send messages in words. It writes them in repetition. And somewhere, out beyond Mars's faint orange path, 3I Atlas continued to drift, or orbit, or watch, carrying inside it an intelligence we might never decode, a purpose we might never be meant to. The silence that followed wasn't an ending. It was an interval, the same pause between signals, waiting for the next rotation, the next flash, the next arrival.